Hello and welcome to my channel. I'm glad you're here. I'd like to know where you are in the world before we start. Where in the world are you watching from? A peaceful bedroom, a train ride that makes you asleep, a nice cup of tea, and a comfy couch. Wherever you are, I hope you're comfy, protected, and ready to slip off into thinking gently. If you enjoyed these calm journeys and want to hear more, please like and subscribe. Helps this sleepy little channel stay afloat. And thank you to everyone who has already signed up. Honestly, your support means more than you know. Now, I'll try not to make tonight's topic so exciting that it keeps you wide awake, but if it does, at least you'll have a better understanding of why particles sometimes act like waves and why reality seems to pause till someone's observing. A little amount to pay for a sleepless night. So let's begin, shall we? What is quantum physics? And why does it so often sound like the universe is making things up as it goes? The reality we know, the one we can see and touch, feels solid, predictable. If you drop a teacup, it falls. If you flip a coin, it lands. If you close your eyes, the moon does not fade. But in the early 20th century, scientists began to investigate closer, considerably closer. And the further scientists probed into the workings of substance, the stranger things became. Light they discovered might act like both a wave and a particle. Particles, it proved out, might exist in multiple places at once until they were measured. And the act of noticing something didn't merely reveal what was already there. It seemed to transform it. This wasn't a quirk of faulty data or fuzzy equipment. It was real, replicable. It destroyed the orderly laws of traditional physics that had held for centuries. Quantum physics wasn't merely a new branch of science. It was a new way of experiencing reality, a bizarre and shimmering one where certainty is replaced by probability, and cause doesn't necessarily precede effect in the way we expect. In this movie, we'll wander lightly through that environment. There's no need to master every equation or memorize every name. We'll proceed slowly, softly, one secret at a time. From the earliest puzzles that moved scientists off their classical perch to the modern questions that still keep physicists up at night. So tuck yourself in, close your eyes if you'd like, and let's begin to explore a world where even emptiness isn't really empty, where everything you thought you knew about reality is just maybe true. At the turn of the 20th century, physics felt almost complete. The laws of motion were understood, thermodynamics was neat, and light was nicely fitted into the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even assume that all the big questions have already been answered. Only a few strange fragments remain to be cleaned up, like dust in the corners of a well-swept room. One of those dingy corners involves a really simple notion. What happens when you heat up an object? When you reheat a piece of metal or a chunk of coal, it sparkles. First red, then orange, then white, depending on the temperature. This luminescence, dubbed black body radiation, arises from how objects release electromagnetic radiation when heated. It was easy to notice, and it seemed like it should be easy to explain. And still, the math refused to cooperate. Classical physics, employing the well-known equations of the time, predicted something unexpected. According to the calculations, when the temperature of a black body grew, it should emit more and more energy at shorter and shorter wavelengths, notably in the UV area. The problem? This prediction led to unlimited energy at high frequencies. A scenario so preposterous and ridiculous, it was nicknamed the UV catastrophe. No amount of tinkering classical equations could stop the math from escalating into madness. Reality simply didn't meet the projections. Something was missing. Enter Max Planck. In 1899, Planck was a German theoretical physicist with a reputation for thorough thought. He wasn't very radical or rebellious. In fact, he sincerely believed in the classical worldview, yet he was also pragmatic. And when faced with the black body radiation problem, he did something subtly innovative. To solve the math, Planck introduced a little odd notion. What if energy couldn't be emitted in simply any amount? What if instead it came in small, indivisible packets? Like coins you can't split in half. These packets would represent the smallest feasible units of energy. He called these packets quanta. This was a radical shift from the continuous notion of energy held by classical physics. Instead of a smooth flow, energy would enter in steps, little jumps that depending on the frequency of the radiation. Planck even developed a constant, now known as Planck's constant, to express the size of these energy packets. It was unbelievably little but mathematically elegant. When he incorporated this idea into his equations, something amazing happened. The endless energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet calamity, and yet he didn't quite believe it. In fact, Planck himself described his solution as a mathematical trick, a smart way to make the numbers behave, but not a description of how the universe actually worked. He thought that future scientists would develop a better explanation that wouldn't require such weird assumptions. Quantization to him was a temporary patch, not essential truth. What he couldn't have known at the time was that his trick would become the cornerstone of a totally new way of thinking. His idea that energy comes in discrete packets set the framework for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It's simple to look back and see this as the moment everything changed. But at the moment, it felt more like a bizarre side note than a revolution. Planck hadn't set out to attack the basis of physics. He just wanted the arithmetic to work. And yet, by introducing quantization, he had lit the first match in what would become a slow blazing fire. One that would eventually change our understanding of light, matter, and the nature of reality itself. This tiny beginning, tucked became a quiet paper published in 1900, and trumpet its importance. There were no grandiose declarations, no sweeping pronouncements, only a little constant, a fresh way of thinking about energy, and a curious little cure for a problem that refused to go away. From that point on, physics would never quite feel finished again. By the early 1900s, light was regarded to be pretty well understood. Thanks to James Clerk Maxwell's equations, scientists had demonstrated that light behaved like a wave, an exquisite ripple in the electromagnetic field. It curved, bounced, diffracted, and interfered just like any real wave should. And after Max Planck's silent introduction of energy quanta, most physicists thought things would settle down into a new, slightly altered normal. But then came a mystery involving metal, light, and startling refusal to comply. It was called the photoelectric effect, and it worked like this. If you shine light on a metal surface, electrons can be expelled from the metal. The idea makes sense. Light delivers energy. Energy kicks out electrons. No huge deal. According to wave theory, increasing the brightness of the light should enhance the energy transferred to the electrons. A brighter wave should shock electrons loose more effectively. That was the expectation. But that's not what happened. In experiments, scientists uncovered something odd. Shining stronger light didn't necessarily expel electrons with more energy. What mattered most was the frequency of the light. If the light was below a particular frequency, even a very strong light, it did nothing at all. No electrons were expelled. But above that frequency, even a faint laser might knock electrons loose with ease. The threshold was acute, and it made no sense in conventional wave theory. This slight irregularity became a full-blown mystery. Enter Albert Einstein. In 1905, a year commonly considered his miracle year, Einstein produced a paper that revolutionized everything to explain the photoelectric effect. He proposed something daring. What if light wasn't just a wave? What if under certain circumstances it behaved like a particle, a little bundle of energy going in a straight line? Einstein proposed that light was constituted of discrete packets of energy, which he dubbed quantum light, subsequently known as photons. Each photon contained a specified amount of energy determined by its frequency. If a photon had enough energy, it could knock an electron loose from a metal surface. If it didn't, no number of photons, no matter how many or how brilliant, could perform the job. It was like attempting to open a closed door with a number of keys, none of which fit. No matter how many you possessed, you weren't getting in. Einstein's idea built directly on Planck's prior work, but went farther. He wasn't just using energy packets as a mathematical technique. He was claiming that light itself was formed of these packets, not as a handy fiction, not as a literal depiction of how light behaves. It was a groundbreaking claim, and not everyone liked it. Many physicists clung stubbornly to the wave model of light. After all, light obviously did exhibit wave-like activity. It diffracted around bends. It caused interference patterns. If light was genuinely constituted of particles, how could it also behave like a wave? Einstein didn't deny the wave character of light. Instead, he recommended something stranger. Light, he claimed, was both a wave and a particle. It may act like one or the other, depending on how you watched it. This dualism wasn't just an odd trick of perception. It was intrinsic to the essence of light itself. Imagine a beam of sunshine filtering through a window. It expands and ripples like a wave bouncing off dust and glass. But zoom in, way in, and you'd find tiny quanta of energy, each with its own frequency, knocking into atoms, transforming the world one collision at a moment. This idea of wave-particle duality is one of the oddest in all of physics. Not because it's complicated, but because it challenges the basic categories we use to describe reality. In the classical world, things are either particles or waves, not both, not neither, and certainly not whatever they feel like being dependent on the situation. But the quantum universe doesn't require permission to make sense. Einstein's photon explanation of the photoelectric effect not only matched the experimental results, it did so beautifully. The energy of each photon relied on its frequency, exactly as Planck had proposed, and it perfectly explained why low-frequency light, no matter how bright, couldn't expel electrons. The individual photons simply didn't convey enough impact. The influence of this notion was immense. In 1921, Einstein got the Nobel Prize in Physics, not for relativity, as many imagine, but because his explanation of the photoelectric effect. That's how significant this finding was. Still, even Einstein found the quantum world unsettling. He notoriously disputed the more probabilistic readings that would follow in later years. God does not play dice with the universe, he once declared. But dice or not, the rules were changing. And at the center of those shifts lay a weird truth. Light, the object that brightens our world, refused to fit into any tidy package. It arrived in quant. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep us curious, and just enough to keep us unsure. What began as a simple experiment with light and metal ended up upsetting the foundations of physics. Because if light could act this way, both continuous and distinct, both spread out and point-like, what else might be hiding in the peaceful nooks of the universe yearning to breach the rules? Imagine this. You put up a table, place a flashlight at one end, and cut two tiny slots in a sheet of cardboard. You shine the light through the openings and look at the pattern it produces on a screen behind them. Not exactly thrilling, right? And yet, in this modest arrangement, 2 holes and a dab of light, we find one of the most mind-bending exercises in all of science. The double-slit experiment has become something of a legend in physics, and not because it's complicated. In fact, it's almost laughably simple. But what it reveals is anything but. Some scientists have even joked that this is the most spectacular science experiment of all time, showcasing a flashlight in 2 holes in cardboard. Let's start with what we'd expect. In the domain of classical physics, waves and particles act quite differently. A wave, like water or sound, expands out. It interferes with itself. Imagine water waves passing between two gaps in a barrier. The waves arise on the other side and overlap, forming a pattern of peaks and troughs that can strengthen or cancel each other out. That's interference. It's well understood and predictable. Now, envision particles like little rubber balls shot into a wall with two apertures. Some go through the left slit, some go through the right. They don't overlap or interfere. On the screen behind the slits, you'd expect to see two clusters of impact points just where the slits are. That's the particle behavior. Straightforward, no surprises. So, what happens when you do this with light? When scientists first beamed light through the two slits, they anticipated it to function like a wave, and it did. The light stretched out and formed an interference pattern, a succession of bright and dark bars on the screen generated by the wave peaks overlapping and canceling each other in certain areas. So far, so wonderful. Light, as Maxwell had predicted, was behaving like a wave. But then things became odd. Using incredibly sensitive equipment, researchers reduced the intensity of the light source until it was firing just one photon at a time. Instead of a steady stream, there were individual particles of light making their way toward the slits one by one. Now you'd expect these lone photons to operate as particles, each going through one slit or the other. And if you wait long enough and collect enough hits on the screen, you should see two bright spots where the particles fell just like those rubber balls. But that's not what happened. Even when sent through one at a time, the photons eventually accumulated up the same interference pattern as before. A pattern that needed waves interfering with themselves. But how might a single photon interfere with itself? Did it go through both slits at once? Was it somehow a wave and a particle at the same time? This was no delusion. The interference pattern remained, implying that each photon had traveled through both slits simultaneously, like a ghost of itself, investigating every potential path till it landed. If it wasn't enough to raise some eyebrows, things got even stranger. Physicists chose to peer behind the veil. They deployed detectors at the slits to observe which path the photon actually took. Surely, they thought, we can just watch and solve this once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they looked, the interference pattern gone. As soon once the detectors were turned on and the photons were detected, the photons ceased acting like waves. They acted like ordinary particles again, landing behind just one slit or the other. No greater meddling. No more phantom wave behavior. It was as if the very act of observation pushed the photon to make a decision. Go left or go right. No superpositions, no hazy in-betweens. Reality had been caught in the act, and it immediately straightened up and acted properly. Turn off the detectors, and the interference reappeared. Switch them back on, and it vanished again. The consequences were astounding. It wasn't that our measuring gadgets affected the photons. These were passive, non-intrusive arrangements. The issue wasn't how we observed, but that we observed it all. It seemed that the simple knowing of the photon's route, the potential to know, was enough to condense its wave-like behavior into a particle state. Reality, in a way, cared whether it was being watched. This wasn't merely a fluke or experimental error. The double-slit experiment has been replicated multiple times using photons, electrons, even molecules produced of hundreds of atoms. Always the result is the same. Left unobserved, these particles operate like waves and interfere with themselves. Observed, they behave like classical particles and fall smoothly into line. And if it seems unpleasant, well, you're not alone. This experiment resides at the very heart of quantum physics, and it resists every endeavor to convey it in familiar terms. It suggests that at the smallest scales, particles don't follow exact routes. Instead, they exist as a spread of possibilities, a dazzling cloud of potential outcomes. Only when a measurement is made does that cloud compress into anything concrete. Some have tried to depict the photon as a wave that separates and reunites. Others favor the language of probability, characterizing the wave function as a tool for predicting outcomes. And still others, in the many worlds camp, envisage each possibility blossoming into its own separate universe. But whatever the perspective, the facts remain the same. Until we observe it, the particle doesn't seem to commit to any one state. What began as a basic test of light has transformed into a profound puzzle regarding the nature of reality itself. Is observation an active part of shaping the universe? Does information have influence over existence? Is reality fundamentally unclear until we beg it to show itself? These aren't merely philosophical questions. They're scientific ones rooted in experiment measured and proven. The double-slit experiment doesn't provide us clear solutions, but it does give us one important insight. The universe at its core is not a clockwork machine. It's a fascinating and sparkling tapestry created from possibilities. And it responds in strange ways to our eyes. With two slits, a light source, and so we've learned that the universe winks at us when we're not looking and stands motionless when we are. In the domain of quantum physics, if there's one piece of arithmetic that's whispered through the entire theory like a secret spell, it's Schrodinger's equation. Now, don't worry. This isn't going to be a math lecture. No one's getting out of bed to fantasize about partial differential equations. But this particular equation is different. It's not merely a string of symbols scratched on a whiteboard. It's the silent heartbeat of the quantum cosmos. Back in the 1920s, physicists were battling with how to define particles that didn't seem to behave like particles at all. Electrons were displaying wave-like patterns. Photons were functioning like probabilistic ghosts. And the old laws of motion, the ones Newton taught us, just weren't cutting it anymore. The universe needs a new sort of language. Enter Schrödinger. In 1926, he proposed an equation that expressed not only how particles moved, but how their wave functions developed over time. It was sleek, compact, and astonishingly effective. And even though it could look like a labyrinth of Greek letters and operators, at its core, it conveys a simple story. It describes how a quantum system modifications. But let's step away from the symbols and get to what actually matters. The important concept here is the wave function, frequently indicated by the Greek letter psi. If that sounds abstract, think about it like this. The wave function is a form of mathematical whisper that gives us everything we can know about a quantum system. Where a particle might be, how probable it is to be there, how it's moving or might be moving. The wave function doesn't give us hard answers. It provides us probabilities. If you visualize a particle as a small dot moving through space, classical physics will draw a nice arrow depicting its exact position and velocity. Schrödinger's world doesn't do that. Instead, it offers us a hazy rippling cloud, a wave that implies the particle is likely to be over here, but it may possibly be over there, and maybe just a little bit up there too. This is where the magic happens. Schrödinger's equation allows us to evolve this cloud over time. It shows how the wave function alters as the particle moves, though it's really more like how the options of its location shift and flow. And when we measure the particle, when we ask, "Where are you?" that wave function collapses. Suddenly, the cloud evaporates, and we get a single, definite response. Here it is right there. But only after we've looked. This wave-based perspective of reality is significantly different from the mechanical vision of the universe that came before. Instead of particles pursuing predetermined trajectories like planets encircling the sun, we now observe swirling fields of probability, full with uncertainty and ambiguity until observation pins them down. But let's pull it down to something more visual. Imagine you're blindfolded and standing in a room. Somewhere in the room, there's a peaceful cat. You can't hear it, can't see it, but you can toss small balls and listen for the sound they make when they land. Over time, you start to construct an image of where the cat might be. Areas having a higher chance, others with less. That mental blueprint you're building, That's like the wave function. It's not a picture of reality as it is, but as it might be. Now, assume you could create an equation that tells you how your map changes over time. Maybe the cat prefers to wander toward corners or sit near warm objects. That equation would be your guide to where the cat is likely to be next. That's what Schrödinger did, except instead of cats, he was thinking about electrons. The actual equation is continuous and smooth. It permits these waves of probability to ripple and alter just like water in a pond. It respects the inherent symmetries of nature, like energy conservation and time evolution. But it doesn't care much for assurance. It tells us what could happen, not what will happen. And what's remarkable is how nicely it works. Physicists have used Schrödinger's equation to describe everything from the structure of atoms to the way molecules connect, from semiconductor behavior to superconductors. It even anticipates strange events like quantum tunneling, where particles pass through barriers they shouldn't be able to traverse. The equation itself is timeless, quietly ticking forward with every moment, presenting a map of the unknowable. One of its most renowned successes was in explaining the hydrogen atom, the simplest atom in the cosmos. Before quantum mechanics, no one could properly explain why electrons circling a nucleus tend to settle into certain orbits rather than spiraling inward or straying off. Schrödinger's equation revealed that electrons aren't whizzing around like tiny planets. Instead, they generate standing waves, stable patterns of likelihood surrounding the nucleus. These are the orbitals you may have seen portrayed as gentle clouds or forms in textbooks. And these clouds are not simply visible metaphors. They indicate the true measurable likelihood of where an electron might be discovered if you decided to look. These aren't orbits. They're present zones. And they exist only because the electron isn't a simple particle. It's a ripple in a sea of probabilities. It's unusual, yes, but it's also incredibly constant. Unlike some theories that need tweaks or caveats, Schrödinger's equation has matured like good wine. It works. It has forecasted time and again the behavior of the extremely little with astounding accuracy. And yet, it stays hauntingly abstract. You can't hold a wave function. You can't see it. But it's there portraying the ghostly potential of everything from an atom in your drink to the electronics in your phone. And then there's the philosophical side. What is a wave function really? Is it a description of our knowledge, or is it a real part of reality? Something that actually exists until it collapses into one outcome. Different versions of quantum mechanics dispute vigorously about this. But the equation itself doesn't take sides. It merely does what it does quietly, reliably, and curiously. Even Schrödinger himself had mixed feelings. While he was proud of the equation, he detested the idea that particles didn't have definite qualities until they were observed. His famous thought experiment involving a cat alive and dead at the same time was designed as a rebuke of the very uncertainties his work had unleashed. He provided us the mathematics of quantum waves, then questioned what those waves really meant. Still, it's hard not to admire what he built. In a world that often demands yes or no, here or there, Schrödinger offers something kinder, a shimmer of maybe, a delicately throbbing clue to what could be. His equation doesn't shout or order. It suggests it flows. And in doing so, it displays a form of the universe that's calmer, subtler, and far more mysterious than we ever imagined. At the tinier scales, motion isn't always motion. Position isn't always position. Uncertainty is more of a luxury than a rule. But thanks to one elegant equation, we can still find our way slowly, mathematically through the haze. In the classical world, the world of apples, bicycles, and bowling balls, you can know where something is and how fast it's going at the same time. It's not even a question. A radar gun clocks the speed of an automobile, while GPS informs you exactly where it is. No misteri, no contradiction. But the quantum world doesn't play by those norms. In the 1920s, Vera Heisenberg introduced a principle so bizarre and so important to quantum mechanics that it still gives students and professionals alike a pause of pause. How might knowing where something is make you unsure about how fast it's going? If you see a train pulling into the station, you know both its position and its speed. Easy. But at the quantum scale, reality doesn't allow that kind of clarity. This isn't about our measurement equipment being awkward or vulgar. It's not a matter of needing better technology. The uncertainty isn't in our instruments. It's intertwined into the fabric of the universe itself. Let's imagine you're trying to watch an electron. You want to know where it is and how fast it's moving. To achieve that, you might shine some light on it. But light is formed of photons, and photons contain energy. When one of those photons touches the electron, it modifies the electron's motion. It's a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You'll undoubtedly locate it, but you'll also destroy it in the process. Still, Heisenberg's message wasn't only about upsetting particles. His principle is integrated into the mathematics of quantum mechanics. Even if you could observe without meddling, watching through some ethereal, non-intrusive way, the ambiguity would still be there. It's not a bug, it's a feature. At the heart of the uncertainty principle is the wave character of particles. Imagine trying to locate a wave in the ocean. You can say where the crest is, but the wave extends out in space. Similarly, a particle like an electron is described by a wave function, a stretched-out cloud of possibilities. If the wave is wide and smooth, you can't identify where the particle is exactly, but you can approximate its momentum fairly accurately. If you narrow the attempt to localize the particle's position, the momentum becomes more ambiguous. The wave grows rough. It's a cosmic trade-off, and there's no way around it. The product of the uncertainty in position and the uncertainty in momentum is always larger than or equal to a tiny number, Planck's constant, divided by 4 pi. That number is quite little. So in our everyday environment, the influence is negligible. You can measure the position and speed of a baseball to remarkable precision without ever coming across quantum boundaries. But at the scale of electrons, atoms, and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behavior of the universe under our senses. If you try to trap a particle in a very limited space to nail down its place, it starts to behave wildly. Its motion becomes exceedingly variable, and it can begin circling unexpectedly. Try to pin it down farther, and it resists even more. It's as though nature doesn't appreciate being informed exactly where things are. This is not an error in the machinery. It's a blur that can't be wiped away. One way to think about it is like attempting to hold mist in your hands. The tighter you squeeze, the less you have. Open your hands a little, and more of it lingers. That's the delicate balance between knowing too much and being compelled to let go of something else. In many respects, the uncertainty principle is a philosophical caution label on the quantum universe. It tells us that knowledge has bounds, not because of human limits, but because of how reality itself is created. We're not dealing with little billiard balls traveling through space. We're dealing with possibilities, probability, and waves that refuse to be pinned down too closely. This idea also explains why atoms don't collapse. You might question why electrons don't simply fall into the nucleus of an atom when opposing charges attract. But according to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there, its location would be well recognized, which means its motion would become infinitely unknown. That would require unlimited energy. Nature says no. So electrons hover not because they desire to, but because quantum principles won't allow anything else. The uncertainty, it produces a kind of built-in resistance, a modest pushback against absolute constraint. This unusual limit also has repercussions for measurements of energy and time or angular momentum and orientation in each pair. Increasing accuracy in one involves relinquishing assurance in the other. It's a universal truth at the quantum level. And yet, there's something soothing about it, too. Uncertainty in this sense is not chaos. It's not randomness run wild. It's a structured ambiguity, a kind of beautiful fuzziness. It gives the universe its texture. It permits particles to tunnel past obstacles, atoms to remain stable, and chemistry to happen. Without it, reality might be too rigid to support life at all. So much of science has been about obtaining certainty, forecasting, measuring, knowing. Heisenberg's insight twisted that desire on its head. He proved that some aspects of nature will always remain just out reach. And that's not a failure. It's just how things are. In an odd manner, the uncertainty principle invites us to make peace with not knowing, to sit quietly with the blur and savor the tenderness of what lies beneath the surface. It's a reminder that the deepest truths are not always sharp-edged, but hazy, rippling, and unresolved. And perhaps that's exactly why they're so gorgeous. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails. A light switches on or off. Your tears hot or cold, though sometimes questionably lukewarm. But in the quantum world, this clean partition of states falls broken altogether. Objects at the smallest scales don't necessarily select a side. They can float in a bizarre in-between, a combination of all potential outcomes. This is the region of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a defined trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time. It's only hidden from you. Quantum systems don't work that way. In the quantum universe, if you flip a quantum coin, it doesn't covertly land on one side while you're not looking. Instead, it enters a condition of superposition, a weighted combination of both heads and tails at once. It isn't undecided. It isn't transitioning quickly between the two. It is actually physically in a state that is both until you observe it. And when you do, and you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face, and your measurement becomes actual. But before you looked, it wasn't simply unknown, it was both. That's a hard pill to take. And it's not only paradoxical, it's deeply weird. Superposition was first introduced as a means to understand the behavior of quantum particles like electrons and photons. These particles, rather than following predictable pathways, exist as wave functions, mathematical formulas that explain probabilities. Each potential condition, a spin pointing up or down, a photon moving left or right, is part of the equation. And all those possibilities coexist until a measurement selects one. You may visualize it like a misty landscape of outcomes. The particle isn't walking a path. It's more like it's spread out, spilling itself across every possible direction it could go. When you interact with it, that fog abruptly snaps into a single area. A precise consequence like lightning illuminating one hilltop in the mist. This thought led to one of the most famous thought experiments in all of physics. Schrodinger's cat. Suppose you place a cat in a sealed cage with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics teaches us that until the atom is detected, it resides in a superposition of decaying and not deteriorated states. And therefore, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was showing the absurdity of applying quantum laws to massive objects. But the notion struck a chord. It painted superposition not simply as an abstract theory, but as something with fundamentally weird consequences for what reality is. And yet, despite all the craziness, superposition is not a fault in the theory. It's not some odd loophole that physicists tolerate. is one of the most potent properties of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message is encoded utilizing combinations of these two states. Quantum computers use qubits instead. And a qubit, unlike a conventional bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them. It's genuinely in a blend of both. This means that a single qubit carries more information than a classical bit. And when numerous qubits are entangled, they can represent a tremendous number of states concurrently. This permits quantum computers to do certain calculations significantly more efficiently than classical ones. It's not magic. It's merely math that plays under quantum rules. Problems involving complicated processes like modeling molecules or optimizing massive networks suddenly become tractable, and it all hinges on the ability of qubits to be in superposition. Superposition also appears in quantum cryptography when it helps ensure that information can't be intercepted without being noticed. In quantum sensing, it allows scientists to detect exceedingly slight changes in magnetic or gravitational forces. These aren't sci-fi dreams. There are real technologies being created right now. But there's a twist. Superposition is delicate. Quantum systems are easily perturbed. The slightest interaction contact the environment. Stray photons, vibrations, even air molecules can collapse the wave function. This process, known as decoherence, is one of the major hurdles in constructing reliable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing in the next room. The superposition dissipates the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They offer us access to probabilities, not certainties, and ask us to reassess what it implies to say that something is. It also leads to a deeper philosophical question. If particles can exist in various states, is that reality or merely a mirror of what we know? Some interpretations indicate that the wave function represents knowledge, our best guess about a system until we measure it. Others say the wave function is physically real, and the particle actually is in various states until it's forced to pick. Either way, quantum superposition asks us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no all at once. That reality at its foundation is not a single thread, but a tapestry of possibilities overlapped and unresolved until observation rips one strand loose. It's bizarre. It's uncomfortable, but it's also gorgeous. Because in this peculiar rule of superposition, we find a universe that isn't rigid, but pliable, not mechanical, but poetic. It's a world that allows for contradiction and uncertainty, not as flaws, but as features. And in doing so, it opens up new ways to calculate, to communicate, to explore, and to imagine what's possible when reality refuses to make up its mind. Imagine you had two gloves, one left-handed and one right-handed. You place each glove into a separate box and mail one to the other side of the world. You don't know which package holds which glove. But the moment you open one and see a left-handed glove, you instinctively know the other must be right-handed. It's not mysterious. It's only logic. The gloves were always one left, one right. No drama there. But quantum entanglement isn't like that. Entangled particles aren't like pricked gloves. They're more like a pair of gloves that don't decide whose hand they are until after you open one of the boxes. And whatever one you open first somehow instructs the other how to behave instantly, no matter how far apart they are. It's not only that the outcome is correlated. It's that the qualities don't seem to exist until the moment you measure one of them. And the act of measuring one directly impacts the other. This is the phenomena of quantum entanglement, and it is one of the oddest, most puzzling elements of the quantum realm. Here's how it works. When two particles interact in a given way, via being created together, clashing or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one in a very genuine sense impacts the other, even when they are separated by large distances. Imagine producing two entangled photons whose polarizations are uncertain unless measured. One can wind up polarized vertically, the other horizontally. But they don't decide ahead of time who receives which. They dwell in a shared quantum state, a superposition of all possibilities. Only when you measure one does the outcome become definite. And at that instant, the other state becomes definite too. Instantly. No signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's claim it's in Tokyo, responds at that precise instant, as though the cosmos simply updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed fully in localization, the idea that physical processes in one spot can't instantly affect objects far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles may coordinate outcomes immediately without exchanging a signal made him terribly uneasy. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, released a paper disputing the completeness of quantum mechanics. They claimed that if quantum physics allows for such instantaneous connections, it must be lacking something. Some secret elements nestle behind the scenes deciding the outcomes all along. To Einstein, the universe should be predictable, orderly, and maybe most significantly local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could identify between quantum predictions and hidden variable theories. And when physicists conduct these tests again and again, quantum mechanics won. Entangled particles do behave in ways that can't be described by local hidden variables. The results are random, yet exactly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, when they improvise together with eerily perfect synchronization. Still, this doesn't mean you can use entanglement to convey signals quicker than light. That would destroy causality, and happily, nature prevents it. While entangled particles reply quickly to each other's measurements, the consequences are intrinsically random. You can't control what result you receive when you measure your particle, which means you can't encode information in it. The instant link is true, but it can't be used for communication. It's like two individuals tossing coins on opposite corners of the galaxy. Each result is random, but somehow when one person flips heads, the other always flips tails. And neither of them knows which it will be until they flip. They aren't sending messages. They're just in tune in a way that defies space. What's genuinely bizarre is that this link doesn't decrease with distance. You could separate two entangled particles by the breadth of a room, a continent, or a light year, and the entanglement would remain. There's no known limit. In reality, physicists have entangled particles over distances of hundreds of kilometers utilizing satellites, and the results continue to uphold quantum theory. But what precisely is entanglement? Is it a type of invisible tether? A shared identity across space? A delicate kind of information spread between particles? The truth is, no one's really sure. Different interpretations of quantum mechanics give distinct insights. Some regard entanglement as a manifestation of information, what we know about the system, not the system itself. Others regard it as proof of a profound non-local fabric to reality. There's even a school of thought that entanglement isn't merely a weird quantum trick, but a basic property of space and time themselves. Some researchers have proposed that spaceme, the very architecture of the world, might emerge from networks of entanglement between small quantum bits. If that's true, entanglement isn't something that happens in space. It's what holds space together. That's a bold notion, and one remains under investigation. But it hints at just how essential entanglement may be, not only to particles, but to the nature of reality. And like many quantum ideas, it's not simply theoretical. Entanglement has practical applications. It's the foundation for quantum teleportation. Not the Star Trek variety, but the real-world movement of quantum states from one point to another. It also underlies quantum key distribution, a way of secure communication that protects privacy. If an eavesdropper tries to intercept the key, the entanglement is upset and the interference is immediately detectable. In quantum computing, entanglement allows for complex computations requiring multiple qubits that can't be simplified to simple separate activities. It's part of what gives quantum computers their power. Not just more speed, but more interconnection. A form of parallelism that ordinary computers can't match. So this creepy activity, once a source of intense distress, is now a cornerstone of cutting-edge technologies. Einstein may have detested it, but even he couldn't refute its mathematical consistency. And while relativity and quantum mechanics still haven't been fully united, both remain remarkably successful in their distinct domains. Entanglement informs us that the cosmos is not simply a collection of separate items bouncing around. It is a densely interwoven web where even distant pieces can be constituents of a shared whole. Where separateness is an illusion, it's not anything we witness in daily life. You don't wake up entangled with your neighbor or discover your coffee reflecting the state of someone else's spoon. But at the slightest levels, this subtle alliance between particles is softly buzzing away everywhere all the time. And maybe that's the strangest aspect of all. That even in a universe of stars and silence, of great distance and emptiness, there are nevertheless echoes of connection, immediate, unseen, and unshakably real. There are few creatures in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature stuck in a thought experiment so unusual that it's often misconstrued for satire. And in a way, it is. It was never meant to be taken literally. But like all good metaphors, it hits on something deeper, a silent uneasiness at the heart of quantum mechanics. The story begins in the 1930s when physicists were grappling with what quantum theory actually meant. The math worked. The projections were accurate. But what was it saying about the world? Was the wave function a real thing? Did particles truly exist in different states before they were measured? Or was this just a tool for calculating outcomes? Van Schrödinger, already famed for his elegant quantum equation, was deeply dubious of how far some physicists were ready to stretch the idea of superposition, especially when it came to measurement. In his view, there was something strange about applying the same rules that governed electrons to ordinary objects, such perhaps a cat. So he asked a question, a dark, playful question. What happens if you take the craziness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Alongside the cat is a tiny radioactive atom, a gear counter, a container of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens at random, the Geiger counter observed. The trigger breaks the container, and the poison is discharged. The cat tragically dies. But here's the twist. Quantum theory informs us that until we perceive the atom, it resides in a superb configuration of both degraded and not decayed conditions, which means the entire system, the detector, the poison, and yes, the cat should also be in a super posture. The cat is both alive and dead. Not symbolically, literally. Least according to some interpretations. Of course, no one has actually put a cat in a quantum box. Schrödinger wasn't suggesting an experiment. He was making a point. He thought it ludicrous to imagine that a cat, an animal with whiskers, warmth, with a distinct propensity for naps, might exist in such a fuzzy, ambiguous state. It wasn't just unusual, it was nonsensical. And yet the concept lasted partially because it captured the essence of quantum indeterminacy in a single unforgettable image. A cat that is both dead and alive till the box is opened. That's a powerful way to convey what it means for a system to stay unmeasured. It's not about indecision. It's about potential. Until observation collapses the wave function, the system has all result, all futures, all states. Simultaneously, Schrodinger's cat isn't truly about cats. It's about what we're allowed to say about the world before we've looked. In quantum mechanics, observation plays a crucial role. Before you measure a system, it resides in a cloud of probability. Each potential state encoded in the wave function. But the instant you interact with it in a way that harvests information, that cloud falls. The system picks a state. One potential becomes actual. All others vanish. But here's the tough bit. What exactly counts as a measurement? Is it the existence of a conscious observer, a mechanical detector, an interaction with the environment? Different interpretations yield different replies, and that uncertainty is part of why the cat still gets so much attention. It requires us to confront the fact that quantum theory, while astoundingly successful in predicting outcomes, is weirdly mute on what's truly happening in between. Some physicists lean on the Copenhagen interpretation. It essentially says, don't worry about that. The wave function gives us everything we possibly know, and measuring just reveals what's already latent in the system. Others like the many worlds perspective, where the cat is both alive and dead in distinct branching universes, and opening the box doesn't compress the wave function. It basically selects your route through the multiverse. There's also the decoherence method, which states that interaction with the environment automatically filters out superpositions, leaving systems that resemble classical. In this view, the cat is never truly in a limbo state, just entangled with so numerous environmental variables that we can't track them all. The superposition becomes inaccessible, not non-existent. Each perspective bears its own intellectual baggage, but all agree on this. Quantum systems do not act like small classical items. They don't stay still and wait to be noticed. They evolve probabilistically in complicated and often non-intuitive ways. So what does this mean for the cat? It means the box isn't just a container. It's a border between the quantum and classical worlds, a stage on which the rules of physics twist into something realm where queries like, is the cat alive, don't have clear answers. Instead, we have to claim the cat is in a superposition of states, living and dead, until we open the box and collapse that uncertainty into something solid. And that's what makes the cat a fantastic metaphor for unmeasured systems. In the quantum world, systems evolve according to the Schrödinger equation. But that evolution doesn't pick a direction. It examines all feasible avenues at once. An electron doesn't travel from point A to point B. It extends across every route, every diversion, until we detect it and limit that muddle to a single outcome. The cat in the box is just a macroscopic method of conveying that. The difference is scale, not principle. And that's what troubled Schrödinger. If the idea genuinely applies to everything, then at some level everything, including ourselves, is part of a superposition. Which leads to one final, somewhat unsettling question. What if the observer is part of the system? If opening the box compresses the cat's wave function, what collapses ours? Where does the observer line stop? Are we just another link in a long quantum chain, collapsing probabilities as we go? Or are we merely riding the wave, surfing on probabilities, never quite sure where the next collapse would lead us? In the end, Schrödinger's cat isn't simply about life and death. It's about knowledge and the weird dance between reality and observation. It's about what it means to say something is when the very act of expressing so might affect the outcome. It's a reminder that in the quantum world, certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside the box. In the common world, barriers are very easy. If you throw a tennis ball at a wall and it doesn't have enough energy to get through, it bounces off. Basic, predictable. The universe responds, "Nice try," and your ball obeys the rules of classical physics like a well-behaved item. But in the quantum world, predictability takes a break. In this bizarre realm, a particle can hit a wall, not have enough energy to get through, and yet still show up on the other side. No shattering, no breaking, no squeezing through cracks. It simply appears as if it concluded the impediment wasn't exactly as sturdy as it looked. This process is termed quantum tunneling. And it's one of those effects that makes you blink, rub your eyes, and wonder if the rules of physics are having a laugh. But tunneling is really genuine. It's measurable, predictable, and important to how the universe works. And strangely, it all boils down to probability. To understand tunneling, we need to examine the concept of wave functions. In quantum mechanics, particles like electrons aren't just small specks whizzing around. They're described by wave functions that represent a spread many possible positions. These waves can spread throughout space, dissipating gradually instead than quitting abruptly. This means that even if there's a region the particle technically shouldn't be able to attain, the wave function might nevertheless spread into that restricted zone, albeit faintly. Now consider a particle approaching a barrier, a location with more energy than the particle itself has. In classical physics, this would be a hard stop. Game over. But the quantum wave function doesn't vanish at the barrier. It tapers off like a whisper fading through a wall. And if the wall isn't too wide or too tall, that whisper can make it to the other side. The particle might not have enough energy to get past the barrier, but its wave function can tunnel through. And if portion of the wave function gets it to the opposite side, there's a modest but non-zero likelihood that the particle itself will show up there too. But it's not magic. It's math. This idea sounds abstract, but it has very tangible repercussions, especially when you shrink your thoughts down to the atomic levels. Take radioactive decay, for example. Some atomic nuclei are unstable. And one of the ways they become stable is by ejecting particles like alpha particles comprised of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a formidable nuclear barrier. According to traditional physics, they don't have enough energy to escape, but they do flee frequently. And quantum tunneling is the reason why inside the nucleus, the alpha particle's wave function expands toward the edge of the nuclear potential barrier. Even though it's unlikely, there's always a chance the particle will tunnel through. Over time, that modest likelihood mounts up until ultimately the particle pops out. That's radioactive decay in operation. Without tunneling, many elements would never decay, and nuclear physics, as we know it, would grind to a halt. Tunneling is also crucial for the most primary energy source in the cosmos, nuclear fusion. In the cause of stars, hydrogen nuclei are squashed together under great pressure and heat. But even under those high conditions, they don't actually have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does. Yet, stars shine and tunneling explains why. At very high temperatures, hydrogen nuclei reach close enough for their wave functions to overlap. There's a slight risk that one will tunnel through the unpleasant barrier and fuse with another. Multiply that minuscule chance by the unfathomable number of particles in a star, and you get a bright continuous fusion process. The furnace that powers everything from sunshine to supernovas. And it's not just distant stars that profit from tunneling. We utilize it right here on Earth in labs, in industries, even in experimental computers. One elegant example is the Scanning Tunneling Microscope, or STM. This gadget allows scientists to view surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip extremely close to the surface of a substance just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By detecting this tunneling current, the microscope builds up a very comprehensive representation of the atomic landscape. What's remarkable is that the STM doesn't contact the atoms. Its imaging is based totally on tunneling, on the ability of electrons to glide quietly through empty space, across a gap, and into a detector. This non-contact technique gives scientists a means to peek into the quantum terrain with amazing precision. Tunneling is also at the heart of certain sorts of electronic components like tunnel diodes and quantum dots. And it's a looming factor in the future of computers. As we decrease transistors to ever-tiny sizes, we're running into quantum constraints. At nanoscale sizes, electrons can tunnel past boundaries that were once deemed solid. It's as if the walls in our circuitry are starting to let particles sneak through when they're not supposed to. This presents both problems and possibilities. On one hand, it causes noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling rather than struggle against it. At its root, tunneling tells us something profound about the nature of reality. We typically think of the world as made of strict boundaries. A particle can go here but not there. A wall is a wall. But the quantum world is more complicated. Barriers are not impenetrable. They are probabilistic. They are ideas, not absolutes. And while we might find that unpleasant, it's also strangely lovely. Because of tunneling, particles are not restricted to the linear pathways we anticipate. They can cheat, slip, blur through the seams of rationality. They remind us that the universe is not a machine built of precise gears, but a glittering tapestry of likelihoods and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they might only glance at the same wall and say, "I believe I'll take the shortcut," and somehow nature permits them. In normal life, we think of nothing as well, nothing. The lack of objects, an empty area, a blank sheet of paper, the area under your bed where socks mysteriously disappear. And when we extend that approach to physics, we frequently envisage the emptiness of space as a pure void, a cold, silent expanse with virtually nothing in it. But in quantum physics, nothing is never really empty. What we term the quantum vacuum is a restless, jittering stage. It's not loaded with atoms or light or music, but it's far from blank. Even when all particles have been gone and no fields are actively doing anything, the vacuum still perceives with energy. At the smallest sizes, space is teeming with invisible activity. Waves rising and plummeting, particles flashing in and out of existence. Is like the hum beneath stillness, the brightness behind darkness. And it all starts with doubt. Heisenberg's uncertainty principle doesn't merely relate to particles' position and momentum. It also pertains to energy and time. That indicates that even in a region of space where energy should be zero, the energy can quickly fluctuate. These fluctuations give rise to virtual particles which appear spontaneously, stick around for a little moment, and then vanish as if they never existed. They're named virtual not because they're imaginary, but because they can't be directly viewed, only deduced through their impacts. These quantum blips can seem like a mathematical oddity, yet they have very significant implications. One of the most remarkable examples is something called the case-mirror effect. It's one of those uncommon situations that enables us watch the quantum vacuum doing something tangible, something measurable. Here's how it works. Imagine inserting two very thin, precisely transmitting metal plates extremely close together in a vacuum, just a few nanometers apart. According to conventional physics, nothing should happen. There's no air between the plates, no forces acting on them. Merely an empty gap. But quantum mechanics argues otherwise. Because the space between the plates is so narrow, Only specific wavelengths of virtual particles can exist there, once things fit perfectly between the limits. Outside the plates, however, there's no such restriction. The result, there's slightly higher pressure from virtual particles outside the plates than between them. And this imbalance causes a force that pushes the plates together. That's the case effect. It's a modest force, but it's been measured. In laboratory experiments, scientists have witnessed these plates attracting each other just as quantum theory expects. It's as if the vacuum itself is softly compressing them, showing because even nothing has a kind of substance. This vacuum energy isn't simply limited to eccentric lab setups. It plays a role across the entire cosmos. In cosmology, there's the idea of vacuum energy density, the belief that the energy of empty space might be responsible for the accelerated expansion of the cosmos. We call this mysterious force dark energy. And while we don't entirely comprehend it, the concept of a quantum vacuum pulsating with energy might be a large part of the puzzle. But there's a catch. The projected energy of the quantum vacuum, according to quantum field theory, is huge. If we tried to calculate the total vacuum energy of the cosmos using what we know from particle physics, we get a quantity that's wildly greater, like 120 orders of magnitude larger than what we really witness. This is commonly termed the worst prediction in physics, and no one has fully found out how to repair it. But it demonstrates exactly how complicated and strange the vacuum actually is. Back at the quantum scale, virtual particles also have a supporting role in other unusual phenomena. In quantum electrodynamics, for instance, the interaction between charged particles is partly mediated by the continual interchange of virtual photons. These exchanges give rise to the electromagnetic force as we feel it. Even the mass of particles like protons is altered by the swarm of virtual quarks and gluons fluttering about inside them. What we think of as stable solid matter is really the consequence of continual interactions with this unseen fluctuating vacuum. And while these particles arrive and fade quicker than we can measure, their influence is everywhere. They modestly modify the energy levels of electrons and atoms. They contribute to the magnetic moment of particles. They're woven into the fabric of every relationship in nature. This might sound like science fiction, but it's been tested. When we update our estimates to include vacuum fluctuations, like in the famous Lamb shift found in hydrogen atoms, we find that the forecasts fit reality with remarkable accuracy. The math is weird. The thoughts are wacky, but the outcomes are solid. In a way, the quantum vacuum is the most fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, existing within it. They ripple and hum against its background like instruments playing on top of a bass line that never stops. Some scientists even suspect that the vacuum provides clues to larger truths. Could it be the genesis of all structure in the universe? Might it contain information regarding quantum gravity, or maybe about spacetime itself? These are open questions, but one thing is apparent. The vacuum is not a passive backdrop. It's active. It's structured. It's packed of potential. Even in the coldest regions of space, when matter is rare and starlight is a memory, the quantum void is still there, quivering, jittering, whispering the rules of existence to everything ready to listen. It's sobering to consider that nothing is never actually nothing. That even in apparent calm, the universe teems with covert activity. In the pauses between periods, in the spaces between particles, in the silence between stars, something is always happening. We live not on a quiet stage, but on one that murmurs beneath our feet. And while we may not hear it with our ears, science has identified the instruments to listen. The vacuum hums, the particles flash, and reality dances to a rhythm we've only just begun to fathom. In the quantum world, reality doesn't necessarily act like a story with a definite beginning, middle, and end. Particles don't merely go in straight directions. They glide in clouds of probability. They superpose, entangle, and sometimes tunnel their way through things that should be solid. But arguably, the most perplexing twist in this quantum tale comes when we ask a very human question. What occurs when we look? This simple act of observing a measurement seems to cause something tremendous, a shift, a transformation in the very nature of the quantum system. This is known as wave function collapse. Before measurement, a particle like an electron or a photon is described by its wave function, a mathematical object that holds all the conceivable outcomes of where it could be or how it might act. That electron isn't in one location. It's in a combination of many possible spots. Its spin isn't up or down. It's both. Its path isn't chosen. It's all of them at once. The wave function is a shimmering probabilistic fog. But then you measure it. You fire up your detector. You ask, where is it? And in that instant, the wave function collapses. The fog condenses. All those swirling possibilities snap into a single reality. The electron is suddenly there in one precise position. Its spin is up or down, not both. And this collapse doesn't seem to develop gradually. It's rather a steady withering of possibilities. It's abrupt, binary. One moment the system is in super posture, the next it's locked into a certain state. As if the universe, after much reluctance, makes a final decision the instant we check. That's odd enough on its own. But it gets weirder because no one knows exactly what caused the collapse. Is it the physical encounter with a measuring device? Is it the conveyance of information? Is it consciousness? A camera? A fly buzzing past the lab? The truth is the collapse of the wave function, though important to quantum theory, is not widely understood. In fact, that might be the biggest mystery in all of contemporary physics. Different interpretations of quantum mechanics try to answer the question in many ways. The most traditional approach is the Copenhagen interpretation championed by Niels Bohr and Vera Heisenberg. In this view, the wave function is not an actual physical object. It's just a tool for predicting probabilities. And collapse happens when a measurement is performed, when we gain information. Before that, inquiring about what's truly happening isn't meaningful. The electron isn't somewhere waiting to be found. It simply isn't somewhere in particular unless we search. It's a practical approach. It makes the math work, but it leaves many scientists disappointed because it doesn't really explain what measurement is or why the wave function must collapse at all. Then there's the multiple worlds viewpoint, which throws collapse out the window totally. According to this notion, the wave function never collapses. Instead, every possible consequence happens, just not in your universe. Measure an electron spin, and the cosmos splits. In one version, it's spin up. In another, spin down. You only experience one of those outcomes, but the others still exist, evolving in parallel. No breakdown, no mystery, just branching realities. It's a radical idea and remarkably consistent with quantum math. But it comes at the cost of multiplying worlds like cosmic confetti. Every measurement, every encounter, every choice, a never-ending spray of realities. It's elegant in one sense, ludicrous in another. Other interpretations seek to make collapse feel more real. In the objective collapse theories, the wave function is a physical phenomenon that collapses spontaneously, arbitrarily, without measurement. It's only that measuring raises the likelihood of collapse. These theories introduce fresh laws or even new physics to explain when and how collapse happens. They're still being tested, but they offer a fascinating notion that wave function collapse might be something nature does, not merely something we perceive. Then there's cubism, a more recent and radical view. It suggests that the wave function doesn't describe the system at all. It describes our beliefs about the system. It's a personal subjective tool for forecasting outcomes. And collapse isn't a physical occurrence, but a mental update. Like learning a new fact and changing your expectations. Reality doesn't alter. You do. Some physicists find that invigorating. Others find it terribly disappointing. After all, shouldn't physics be about the cosmos, not our opinions? There's mentioned the role of decoherence, which doesn't explain collapse directly, but helps understand how superp situations seem to vanish in huge systems. When a quantum system interacts with its environment, even just a few stray photons, it becomes entangled with the world around it. That entanglement causes the interference patterns we identify with superp locations to disappear. To us, the system seems like it collapsed, even though it hasn't actually picked a state. Decoherence explains why cats don't stay both living and dead, but it stops short of saying how one outcome becomes true. And there we sit. More than a century after the birth of quantum theory, wave function collapse stays a ghost in the machine. The math works perfectly. We can foresee outcomes with amazing precision. But what exactly collapses? When? Why? Is collapse even real? Or are we just witnessing the boundaries of our own comprehension, and there's no scarcity of ideas? Some scholars say we need a new theory of measurement or a deeper theory of reality that goes beyond quantum mechanics. Others are content with the ambiguity. They say the predictions work and the rest is philosophy. But philosophy matters notably here because the subject of wave function collapse isn't only about particles. It's about what the universe is. Is reality intrinsically probabilistic? Is it observer-dependent? Is it continually branching? Is it influenced by information, by consciousness, by something we've yet to discover? And how much can we ever fully know? You might think of collapse as the instant the quantum world dips into the classical, a kind of phase transition like water freezing into ice. But unlike water, the norms of this change are ambiguous. We don't know the temperature. We don't know the pressure. We only know that at some point the fog gets a shape and potential becomes presence. It's easy to become lost in the metaphors. Is the wave function a veil? Dream? A menu of futures waiting to be chosen? Perhaps it's all of those and none. Perhaps what collapses is not the wave function itself, but our illusion that the universe must always be definite, always be one thing or another. Maybe the universe is comfortable being unsure. Maybe we're the ones who insist on conclusions. What happens when we measure? Maybe the better question is, what do we think happens? And are we prepared for the answer to be stranger than we thought, but truer than we imagined? If quantum physics had a hometown, it would probably be Copenhagen. Not because of the scenery, though Denmark does have a wonderful abundance of windmills and bicycles, but because it's where some of the weirdest concepts in physics were first seriously examined, argued over, and silently accepted. At the heart of this story is Niels Bohr, a Danish physicist with a lovely disposition and a fondness for elaborate, complicated phrases. Bohr helped shape one of the most important viewpoints of quantum physics, a stance that came to be known as the Copenhagen interpretation. The notion is deceptively simple. In fact, that's part of its attractiveness. According to the Copenhagen approach, quantum systems don't have definite properties until they're measured. An electron doesn't have a fixed position. A photon doesn't commit to a certain polarization. A particle doesn't choose a state unless an observation forces it to. Before measurement, reality is a nebulous cloud of possibilities, a probability wave. Measurement doesn't only disclose something that was previously there. It creates the consequence. In other terms, reality isn't quite real unless we ask it to be. That's a strong remark, and it's the kind of stuff that makes philosophers sit up and physicists reach for coffee. But Bohr and his colleagues weren't aiming to make the universe enigmatic for the sake of it. They were attempting to make sense of experimental results. Every time they tried to treat particles like small billiard balls, the arithmetic fell apart. But when they viewed particles as probability waves that only resolve upon measurement, things clicked into place. The wave function in this view isn't a physical object. It doesn't describe a particle's real position or momentum. Instead, It encodes everything we can know about the system. It's a mathematical inventory of possibilities, not a map of what is. This leads to one of the Copenhagen interpretation fundamental claims. Questions about a system state before measurement are worthless. Asking where the electron was before you measured it doesn't make sense because location only becomes a meaningful term after the measurement. Reality is not something you peel aside like a curtain. It's something that snaps into focus the moment you look. It's not that the particle was masking its genuine character. It simply didn't have one yet. Understandably, not everyone found this satisfying. Albert Einstein, for one, was famously uneasy with the idea. He wanted a cosmos that existed independently of whether anyone was witnessing it. He believed in a fundamental reality, objective and predictable, even if it was currently obscured from view. To Einstein, the Copenhagen interpretation sounded like saying, "The moon doesn't exist unless you're looking at it." Bohr disagreed, but he didn't try to propose a big metaphysical solution. Instead, he embraced a form of pragmatic ambiguity. His position was that quantum theory informs us what we can say about nature, not necessarily what nature is. The role of science in this view isn't to find what's truly out there, but to summarize the outcomes of experiments as precisely as possible. If that sounds a little disappointing, you're not alone. The Copenhagen interpretation is often criticized as being more of a prescription than a description. It tells you how to utilize the equations. It informs you what the outcomes will be, but it doesn't tell you what's truly going on behind the scenes. This gave rise to the now infamous saying, "Shut up and calculate." It's not a quotation from Bohr himself, but it catches the spirit of many professional physicists. The notion is, stop worrying about the metaphysical consequences and just utilize the theory. It works. It offers precise predictions. Isn't that enough? And to be fair, the Copenhagen approach does work. It's the default interpretation used in innumerable textbooks, labs, and classrooms. It supports the construction of semiconductors, lasers, and quantum computers. It has never failed an experimental test. For many scientists, that track record surpasses any philosophical concern. But nonetheless, the uneasiness stays. If reality only becomes real when measured, what does that suggest about the universe before observers existed? Did nothing have defined properties before conscious life arrived? Was the early cosmos in a form of suspended animation waiting for someone to look? Most physicists would reply no. The Copenhagen interpretation doesn't require a conscious observer, merely an interaction with a measurement device or with the environment. Observation in this case is just a technique of obtaining information from a quantum system in a way that pushes it to take a side. But even this leads to more questions. What counts as a measurement? At what point does the wave function collapse? Why does the universe follow this peculiar rule at all? The Copenhagen camp tends to answer with a shrug and a smile. The hypothesis doesn't explain why collapse happens. It only indicates when. If you want a deeper explanation, you'll need to go elsewhere. And many have competing interpretations like many planets, pilot wave theory, and objective collapse models all try to present a more complete picture. Each tries to preserve some classical intuition that reality exists independently, that cause leads to effect, that observation doesn't get special consideration. But each of these choices comes with its own complexity. Copenhagen, by comparison, is lean. It doesn't introduce hidden variables. It doesn't multiply worlds. It only lays forth a set of principles. Calculate the wave function, apply the measurement postulate, and anticipate the outcome. Simple, direct, effective. Maybe that's its attraction. In a world full with odd possibilities, the Copenhagen interpretation gives a kind of tranquility. It's not aiming to unravel every riddle. It's content to describe the world we can see, measure, and interact with without professing to know the deeper machinery behind the curtain. And maybe that's enough. Bohr often spoke in complex, almost beautiful phrase. He famously observed, "Those who are not astonished when they first come upon quantum theory cannot possibly have grasped it." He knew that the Copenhagen method wasn't about making peace with reality. It was about making peace with uncertainty. Quantum mechanics is odd, but rather than force it into something clean, the Copenhagen interpretation enables us to embrace such weirdness and to work within it without demanding that the world explain itself. It's not a final explanation. It's a quiet rulebook, a reminder that in the quantum realm, simplicity and discomfort often travel together, and that sometimes the best we can do is shut up and calculate. Imagine you're holding a coin between your fingers. You flip it. It spins across the air, glistening in the sunshine, and lands with delicate clink. Heads. But according to one interpretation of quantum mechanics, something else happened also. Somewhere, not here, but still real, the identical coin landed tails, and someplace else again it landed on its edge, rolled off the table, and landed under the couch. Every potential consequence of that flip unfurled, not as a maybe, not as a probability, but as a true branch of reality, and you just happen to find yourself in the one that saw heads. This is the weird and brilliant idea underpinning the many worlds interpretation of quantum physics. It originated as a thinking experiment, an alternative method of looking at the famed wave function collapse problem. You may remember the wave function, the mathematical cloud of possibilities that defines everything about a quantum system. In the classical Copenhagen approach, when you make a measurement, the wave function collapses and one possibility becomes genuine. But what if it never collapses at all? In 1957, physicist Hugh Everett III suggested a novel hypothesis. Maybe the wave function is always evolving smoothly and deterministically. Maybe when you measure a system, you don't push it to choose a single outcome. Instead, you split. The universe splits. Every potential scenario plays out, but each in its own distinct branch of reality. It sounds dramatic, like something from science fiction. But Everett wasn't creating a story. He was performing math, and his interpretation of quantum mechanics is mathematically equivalent to the conventional version, just without the extra rule that says collapse happens when you watch. In his opinion, the wave function never collapses. It only branches. Here's how it works. Imagine an electron with two potential spin states, up and down. If you measure its spin, conventional quantum physics says the electron is in a superposition of both states until measured, at which point it chooses one. Everett argues no selection necessary. Instead, the measurement leads the system and the observer to split into two correlated branches. In one, you witness spin up. In the other, spiral down. Both endings are genuine. Both versions of you exist, each in a different branch of the cosmos. No randomness, no collapse, just a growing, branching tree of reality. This may sound like a formula for science fiction overkill, parallel universes, doppelgangers, limitless duplicates of everything. But the many worlds interpretation doesn't rely on fiction. It doesn't offer novel physics or untested forces. In fact, its central attractiveness is that it keeps exclusively to the mathematics we already employ. It simply refuses to add the extra assumption that something wonderful happens when you look. To fans of many worlds, this is its power. The premise is odd, yet the math is clean. Of course, not everyone is comfortable with this. For one thing, if the world is continually branching into other realities, where do all these universes go? Are they stacked on top of each other, drifting in some higher dimensional multiverse? The theory doesn't say. And that's part of the philosophical tension. Many worlds isn't a theory regarding the organization of space. It's a statement about how quantum systems evolve. The other branches are genuine, but they don't interact with ours. Once a split occurs, the branches decohere, meaning they no longer interfere with each other. They become, for all practical purposes, invisible. That makes the hypothesis hard to verify directly. After all, If we can't observe the other branches, how do we know they're there? That's the primary criticism. Many worlds may be elegant, but is it falsifiable? Can you prove it wrong? Supporters believe that's the wrong issue. They say it's not about adding new predictions. It's about not introducing unneeded assumptions. If the wave function evolves smoothly according to the Schrödinger equation, and that equation never involves collapse, then why suppose collapse occurs at all? Occam's razor, typically summarized as the simplest explanation, is usually the true one, cuts both ways here. Copenhagen keeps the cosmos small by adding collapse. Many worlds keeps the arithmetic simple by embracing a very huge universe. But is that cosmos too large? Let's take a soothing moment to ponder the scale. Every time a quantum interaction has several alternative outcomes, the universe branches that encompasses not just lab experiments, but molecular collisions, radioactive decays, photon emissions, and everything else. The cosmos isn't dividing every now and then. It's branching constantly, massively, unimaginably. But in the same way, we don't feel the Earth spinning under our feet. We don't feel the branching. To us, it's undetectable, seamless. We simply see one outcome as if that's all there ever was. It's also vital to mention that in many worlds, these other realities aren't parallel lives in the sci-fi sense. You're not jumping between them. You don't get to meet your other self. Each branch is causally isolated from the others. There's no communication across the gap. No peeking at other versions of yourself eating soup instead of salad. Once a split occurred, it's irreversible. This avoids a lot of the philosophical issues that come with wave function collapse. There's no need to specify what counts as a measurement or when reality becomes real. Everything evolves smoothly. Measurement is only entanglement. You and the system have become linked, and the universe unfolds accordingly. But that serene elegance also comes at a cost. If every possible consequence happens, then why do we feel that just one outcome occurred? Why does it feel like the coin landed heads and not tails? If all outcomes are real, what does probability even mean? Many worlds redefines as probability not as the likelihood that anything will happen, but as a measure of how much you ends up in each branch. It's a minor shift. Instead of asking what are the odds, you question what fraction of my future selves view this result. It's not intuitive, but neither is quantum mechanics in general. And despite all its strangeness, many worlds has prompted deep, serious inquiry. Some physicists feel it could aid unified quantum theory with gravity. Others regard it as a foundation for understanding quantum computers where superpositions and entanglements do computational heavy lifting across possible states. It also offers a unique form of comfort or disco depending on your perspective. In this interpretation, no outcome is ever fully lost. Every possibility exists somewhere. The decisions you didn't make, the chances you didn't take, they're all still out there playing out in parallel timelines, not only hypotheticals, but real physical occurrences in real physical environments. It's not meant to make you feel small. If anything, it's a reminder that the cosmos may be more giving than we expected. Not just a particular story unfolding, but a vast and dazzling library with every possibility written into existence. So when you conceive of multiple universes, don't image a noisy stack of cartoon realities. Picture a peaceful branching tree. Each twig a road, each a planet, each consequence a poem written in the language of physics. And all of them in their own way accurate. Imagine throwing back the curtain on everything. The stars, the oceans, your chair, your hand, even the light dropping lightly on your pillow. What if all of it, all matter and energy, wasn't made of tangible things at all? What if the most fundamental element of reality wasn't substance at all, but vibrations, waves, unseen ripples spreading across landscapes that fill all of space? Welcome to the tranquil yet profound world in quantum field theory, where the universe is not created out of particles but out of fields that shimmer beneath everything. Let's start softly. In classical physics, a field is something that assigns a value to every point in space. A familiar example is the electric field, an unseen force that tells a charged particle how it should move. If you inject a positive charge into an electric field, it feels a push. That's the field at work. Fields are smooth, continuous, and fill the world like invisible jelly. Now, quantum mechanics comes along and sprinkles uncertainty onto the image. It argues fields don't just sit there softly. They vary. They buzz even in the absence of any genuine particles. Every field, electric, magnetic, gravitational, is quantum in nature. It jiggles even when it seems empty. Even the vacuum, as it turns out, isn't truly tranquil. It's restless. And here's the leap. In quantum field theory, or QFT, everything is a field. Every particle you've ever heard of, electrons, photons, quarks, neutrinos, is merely a minuscule blip in its related field. A particle is not a little marble flying traversing space. It's a localized ripple, a bump, a jitter in an underlying field that fills all of existence. Let's take the electron. Somewhere in space is the electron field, a quantum field that exists everywhere. When you view an electron, you're not looking at a separate self-contained item. You're watching a particular quantized excitation of that field. The field got excited in a confined way, and that's what you name an electron. Same goes for photons. The electromagnetic field fills all of space. When a light particle zips by, it's not a little bullet. It's a ripple, a little vibration in the electromagnetic field. Turn the knob on that ripple exactly right, and you get visible light. Turn it differently, and you get microwaves or X-rays. But it's all simply styles of dance in the same field. There's a field for every known particle. Quark fields, gluon fields, Higgs fields. Even the elusive graviton, if it exists, would be a ripple in the gravitational field. So where did our old buddy, the particle, go? In a sense, particles are a handy fiction, a way to define the behavior of fields in certain scenarios. When the field is localized and the wind behaves as a single packet of energy, it's convenient to name it a particle. But that's simply our word for a behavior. The field is fundamental. The ripple is what we observe, but the field is what's truly there. This adjustment in viewpoint is substantial. It turns the world from a Lego set consisting of small bits into something more like a symphony, an infinite orchestra of overlapping tones with reality developing from their interference and harmony. Quantum field theory also explains certain strange elements of quantum mechanics that traditional quantum theory struggles with. For instance, how do particles produce and destroy themselves in high-energy reactions? Simple. They're just field excitations. Smash enough energy into a patch of space, and you can jiggle a field hard enough to spawn a new ripple. That's how particle collisions at places like CERN may produce totally new particles out of what feels be thin air. And what about antiparticles? The electron's shadowy twin, the positron. In quantum field theory, antiparticles are essentially another mode of excitation in the same field with opposing features. Nothing weird, simply more symmetries in the rippling. Here's a very nice twist. Forces themselves are mediated by fields. The electromagnetic force, it's the outcome of charged particles exchanging photons, waves in the electromagnetic field, the strong force. It's gluons vibrating in the gluon field, binding quarks together. Gravity, if it's ever successfully quantized, would require small ripples in the gravitational field. Gravitons. Even empty space isn't actually empty. Quantum field theory indicates that fields are never entirely still. They're always jittering with vacuum fluctuations. These oscillations can have significant consequences, like the Casimir effect, when two metal plates placed very close together in a vacuum perceive a force drawing them together produced by variations in the field's energy between them. There's something beautifully tranquil about this picture. The idea that space itself is not a passive backdrop but an active participant. Every point in space is alive with possibility. Every particle, every interaction, every ray of light or explosion of energy is just the field expressing itself. Of course, quantum field theory is difficult. It's not something you can easily compute on a napkin, unless your napkin is the size imagine a blackboard and your chalk is designated Feynman diagrams. But the conceptual takeaway is clear. Nature at its most fundamental is not made of stuff. It's made of excitations, patterns, energy arranged in space and time. Even mass, the persistent hefty quality of stuff, is in many circumstances an emergent property of field interactions. The Higgs field, discovered experimentally in 2012, is responsible for providing many particles their mass. Particles interact with this field like swimmers moving through molasses. The more resistance they feel, the more mass they appear to have. So here we are ensconced in a universe of fields. You, while you listen to this, are a tiny pattern in the electron field, the quark field, the photon field. Your ideas are patterns of excitation. The very atoms of your body are nodes in a cosmic meshwork of fields humming in invisible harmony. You don't end at your skin. The fields that identify you spread out into the universe. There is no sharp edge, no firm boundary, simply softer or stronger ripples dissipating into the greater sea of quantum reality. Quantum field theory doesn't just describe the universe. It is the universe. Or at least it's the best map we've made so far. A map where reality is not comprised of things banging into each other, but of fields intertwined in a dance too quick, too subtle, and too beautiful to ever fully catch. And if you're still awake, you might be wondering, if everything is a ripple in a field, what are we rippling through? That, dear listener, is a question for another dream. If the cosmos came with a cookbook, the standard model of particle physics would be its ingredient list, minus a few mysterious spices like dark matter and dark energy. It's a surprisingly compact recipe, elegant in its arrangement and just a little bit crazy in its naming practices. But for all its eccentricities, this model is one of the most successful theories in the history of science. It informs us what the cosmos is comprised of, how those pieces interact, and why reality looks and behaves the way it does. Let's start by introducing the cast. At its essence, the standard model is a collection of constituent particles. Particles that, as far as we can determine, cannot be broken down into anything smaller. You can think of them as the essential building pieces of matter and force linked together by the threads of quantum fields. There are three broad families: quarks, leptons, and bos. Quarks are the material of protons and neutrons, the solid core of atoms. There are 6 types or flavors of quarks: up, down, charm, weird, top, and bottom. Yes, those are their genuine names. Physicists can do the most accurate math imaginable, but naming things, that's where the pandemonium blooms. The up and down quarks are the lightest and most plentiful. A proton is formed of 2 ups and 1 down. A neutron is comprised of 2 downs and 1 up. That means everything you see, touch, or are is largely up and down quarks, plus electrons, which we'll meet in a moment. The other quarks, charm, strange, top, and bottom, are heavier and frequent, and usually show up in high-energy situations like particle accelerators or cosmic radiation. They're like the special guest stars of the particle world. Flashy, short-lived, but important in the grand scheme. Next, we have the leptons. This category includes the electron, which you've encountered numerous times before, zipping around atoms, carrying electricity, and basically making life possible. Electrons also have cousins. There's the muon, which is like a heavy electron, and the tau, which is even heavier yet. Like the exotic quarks, these larger leptons don't persist long in the nature, but they show up in high-energy reactions and leave significant traces. Each of these charged leptons comes with a neutral mate, the neutrino. There are three of them, one for each flavor, and they're tremendously light, tremendously swift, and incredibly aloof. Neutrinos hardly interact with matter at all. Billions pass through your body every second without leaving a trace. They're the introverts of the universe, constantly present, rarely observed. So far, we have 6 quarks and 6 leptons organized in 3 tidy generations. That's 12 matter particles complete, all dancing on a stage provided by quantum fields. But matter alone doesn't make a universe. We require forces, the principles that control how these particles interact. That's where the bosons come in. Bosons are the force carriers. Each fundamental power has its own messenger particle, a form of quantum handshake that tells other particles what to do. For the electromagnetic force, the carrier is the photon, the particle of light. It's massless. It moves at the speed of light, and it keeps electrons bonded to atoms. Without photons, chemistry and breakfast wouldn't exist. The weak nuclear force responsible for processes like radioactive decay has 3 boss: the W+, W-, and SBOS. Unlike the photon, these are hefty. So heavy, in fact, that they're only implicated in interactions at relatively short ranges. They help transform neutrons into protons and vice versa, fueling the fusion that fuels stars. Then there's the strong nuclear force, the glue that holds quarks together inside protons and neutrons, and bonds those protons and neutrons inside atomic nuclei. Its carrying particle is the gluon, a massless but energetic force bearer that comes in 8 variants. Gluons are like a very hyperactive group of toddlers in a ball pit, constantly exchanging energy, never sitting still, and fully responsible for why your atoms don't fall apart. Finally, there's a new B, the Higgs boson. This particle was proven experimentally in 2012 at CERN and awarded a Nobel Prize. The following year, the Higgs boson is the manifestation of the Higgs field, which pervades space and gives mass to many of the other particles. Without the Higgs mechanism, the conventional model would describe a very weird universe, one where most particles whizzed around massless, unable to cluster together into atoms. So to reiterate, we have 12 matter particles, 6 quarks and 6 leptons and 5 force-transporting bosons: photon, WZ, gluon, and Higgs. All of this is the regular model, and it works wonderfully. This model has predicted the results of many experiments with incredible precision. From the behavior of particles in colliders until the decay rates of radioactive isotopes, the traditional model just continues being true. It's not perfect, but it's remarkably stubbornly good at what it does. Of course, it has a few holes. For one, it doesn't incorporate gravity. The standard model is a quantum theory. While gravity is best characterized by Einstein's general relativity, a classical theory. Merging these two frameworks is one of the most unsolved problems in physics. Then there's dark matter. Astronomical observations imply that most of the matter in the cosmos is invisible and doesn't interact with light. The conventional model doesn't account for it. None of its particles can explain the gravitational effects we observe in galaxies. And let's not forget dark energy, the mysterious power pushing the universe's accelerated expansion. That also is outside the regular model's jurisdiction. In fact, the typical model captures just approximately 5 of the universe. But what if 5 it is? Every particle, every interaction, every explosion of light, every breath you take, it's all enclosed within this dazzling mesh of particles and forces. It's often said that the usual model is complete yet unsatisfying. It's like finishing a puzzle, only to that the image on the box was merely a small portion of a much larger picture. But still, what's there is astounding. Elegant symmetries, complicated interactions, and mathematical patterns that bind particles in ways that hint at a greater unity. Some physicists predict that all of this quarks, leptons, BOS may someday be united under a grand unified theory, or perhaps a theory of everything. These dreams may lie beyond the reach of current research. but they're guided by the same spirit that built the Standard Model. The concept that nature is knowable, that patterns lie underneath the chaos, and that even the wildest forces obey quiet laws. So the next time someone asks what the cosmos is comprised of, you may smile and respond, mostly quarks, a few leptons, and a handful of xants. And then for fun, you can add, oh, and don't forget the Higgs field. Without it, none of this would have any weight. That's not the complete story, but it's a fairly decent starting chapter. At the crossroads of stunning complexity and mathematical precision rests a theory that might just be the crown treasure of physics. Quantum electrodynamics, or QED for short. It's the framework that describes how light and matter interact. And it does so with such perfection that even the pickiest decimal places stand in wonder. At its core, QED depicts the quantum dance between electrons and photons. Every flicker of light, every spark, every push and pull between charged particles. It's all a show staged by the rules of QED. And somehow, despite involving an unlimited number of conceivable interactions and mind-bending probabilities, the ultimate response is it delivers match experiments with incredible accuracy. We're talking about forecast confirmed to greater than 1 part in a billion. That's like measuring the width of North America to within the thickness of a human hair and being right. So, how does QED manage this? Let's start with the problem it addresses. In the early 20th century, physicists recognized that electrons interacted with the electromagnetic field. When an electron accelerates, it emits light. When it absorbs light, it changes energy levels. But calculating the exact behavior of these interactions at the quantum level turned out to be a nightmare. The equations blasted up. Infinities appeared where they shouldn't. You try to work out how an electron emits a photon, and the math would vomit forth crap like unlimited energy, which is not helpful unless you're trying to boil the entire universe. Enter a physicist with an impish grin and a penchant for bongo drums, Richard Feynman. Feynman, along with Julian Schwinger and Suniro Tominaga, found a way to make QED behave. But Feynman went one step further. He made it visual. He devised Feynman diagrams, a graphical technique to depict particle interactions that reduce sophisticated quantum computations into very infantile scribbles. In these graphics, particles are lines. Time flows from left to right. An electron might enter from one side, emit a photon, and then continue on its route. That photon might zoom off and hit another electron, or loop back around and affect the same one. Each of these has a mathematical expression, and QED instructs you to sum them all up. Not simply the most likely one, but every potential way the contact could happen. That includes some really weird possibilities. An electron emits a photon which forms an electron-positron pair, which subsequently annihilates and becomes another photon which is absorbed again. These are known as virtual particles. They exist solely in the mathematical interludes between genuine quantifiable events, but they shape the outcome in very meaningful ways. This is where QED becomes less like physics and more like poetry written in maths. It doesn't merely account for what does happen. It accounts for everything that could happen. Every zig, every zag, every loop and squiggle is part of the final answer. And somehow when all those options are stitched together, the outcome is a prediction so precise it could tell you how an electron would behave on the far side of the galaxy down to the finest decimal. One of the triumphs of QED is its explanation of the anomalous magnetic moment of the electron. The electron has a small magnetic field. Like a tiny bar magnet, classical physics predicts its strength, but quantum influences change it only a little. QED calculates this tweak and matches the experimental result to over 10 decimal places. It's not just nice, it's breathtaking. The theory also clearly explains phenomena like Compton scattering when a photon bounces off an electron, Bremsstrahlung where a particle releases radiation when slowing down, and pair creation where light can convert into matter and antimatter. All of these processes, which sound like sci-fi spells, come easily out of the QED framework. It's worth remembering that QED doesn't stand alone. It's the quantum field theory that describes electromagnetic, but it's also the template for other quantum field theories. The strong force has its own version termed quantum chromodynamics. The weak force is handled by electroweak theory, which unites electromagnetism and the weak interaction. But QED came first, and it set the standard. And here's something charming. Despite its mind-melting math, QED is deeply intuitive once you get the hang of it. Feynman himself often claimed that the rules of quantum electrodynamics could be written on the back of a napkin. In his signature style, he simplified it down to this. Particles take every possible path, each with a probability amplitude. You square the sum to discover the actual likelihood, and that's it. The rest is merely bookkeeping. This concept that nature examines every path is at the heart of the quantum worldview. An electron doesn't just go from point A to point B. It takes every route through every obstacle around every tree and beneath every bridge all at once. The universe is calculating all of those options, and QED is how we peek into that process. It's also a testament to how bizarre quantum physics can be without breaking out. You would think, surely a hypothesis this odd must have limits. And you'd be right. QED doesn't contain gravity, and therefore doesn't explain dark matter. But inside its area, it rules supreme. It is quite simply the most accurately tested theory in the history of science. Even Feynman, who while famously suspicious of excessive adulation, recognized that QED was amazing. But he also urged us not to get too comfortable. Nature, he loved to remark, always has more up her sleeve. And while QED might be the best theory we have, it may not be the best theory we can have. Still, for now, it's a masterpiece. A theory that begins in convoluted math and philosophical frustration and emerged as a clear, exact account of the quantum heartbeat of the universe. Light and matter interacting in an endless whisper expressed with such beauty that even the decimals look impressed. And in that murmur lays the light from distant stars, the pulse of your smartphone screen, and the faint illumination of a bedroom lamp, all orchestrated by a theory so inconspicuous you barely notice it working. But it's there in every flicker, every reflection, every breath of illumination. Quantum electrodynamics, a quiet success, a dance written in fields and photons performed billions of times per second and always without fail on cue. If classical computers are like properly educated librarians, efficient, organized, and great at flipping through books one page at a time, then quantum computers are more like incredibly odd poets who read all the texts at once in overlapping murmurs and somehow still discover the answer. It sounds like magic, and in some ways it feels like that. But quantum computing is real, and it's founded on the same odd concepts that make up the heart of quantum physics. To learn what creates a quantum computing different, you first need to meet the bit's stranger relative, the qubit. In a classical computer, everything boils down to fragments. A bit is a binary unit of information. It can be either 0 or 1, like a switch that's off or on. These bits are the building blocks of everything your computer does, from watching media to calculating your taxes. And traditional computers are great at manipulating lots of bits extremely quickly. But a qubit, short for quantum bit, doesn't only dwell in a state of 0 or 1. Thanks to the magic of superposition, a qubit can be in a mix of both states at once. Imagine a whirling coin that's neither heads nor tails until you stop it and observe the result. While it's spinning, it includes the possibility for both outcomes. This signifies that a single qubit holds more than one state simultaneously. And when you add more qubits, the strength of that superposition develops enormously. 2 qubits can accommodate 4 possible permutations. 3 qubits hold 8. 20 qubits above 1,000,000. With enough kits, a quantum computer could in theories investigate an enormous number of alternatives simultaneously. That's the core notion behind quantum computing. Parallelism. While a traditional computer tests each way one by one, A quantum computer analyzes several paths simultaneously, though not in a method that provides you all the answers instantaneously. The key is in controlling the system so that when measured, the right answer is the most likely to appear. It's not brute force guessing. It's more like changing the probability landscape so the proper solution climbs to the top. But there's another quantum trick up its sleeve: entanglement. When qubits become intertwined, the condition of one is linked to the status of another, even across distances. This allows for complicated relationships between qubits that classical bits simply can't imitate. It's like a dance between particles. If one twirls, the other twirls too, no matter how far apart they are. This entanglement permits quantum computers to accomplish operations that would require traditional machines significant amounts of time and energy. For certain challenges, like modeling molecules or factoring big numbers, quantum techniques offer enormous speedups. But now comes the point where we slow down and breathe a little. Quantum computers are not going to replace your laptop anytime soon. They are specialized instruments, not general-purpose equipment. For duties like browsing the web or editing a video, your classical computer remains the reigning champion. In truth, creating and running a quantum computer is hard. Qubits are exceedingly sensitive. They can be disrupted by tiny vibrations, variations in temperature, even stray magnetic fields. Maintaining a qubit's coherence, its capacity to stay in superposition and entanglement demands utmost care. Many systems must be cooled to temperatures near absolute zero. That's colder than deep space. And then there's error repair. In traditional computers, if a bit flips abruptly, it's quite straightforward to identify and repair. In quantum systems, it's more difficult. You can't simply copy a qubit state without altering it, thanks to the no-cloning theorem. So researchers have had to design innovative techniques leveraging numerous physical qubits to protect one logical qubit. It's like covering your whispering poet in layers of soundproof shielding so they can resume reciting without disturbance. Despite these limitations, progress has been impressive. Companies and research institutes have created quantum computers with tens to hundreds of qubits. Some have established quantum supremacy, accomplishing operations that would take a classical machine an impractical amount of time. Others are creating systems known as NISQ devices, short for Noisy Intermediate Scale Quantum, which examine what we can do with imperfect but still usable quantum machines, and there are actual world applications being researched. One potential field is quantum chemistry. Simulating the behavior of molecules at the quantum level is exceedingly challenging for classical computers, yet quantum machines are naturally equipped for it. This could transform material science, medicinal development, and possibly battery technology. Another fascinating subject is optimization. Solving challenges with several competing variables, like selecting the optimal delivery routes or distributing resources efficiently. Quantum algorithms may be able to find solutions faster and with fewer steps than traditional methods. And then there's cryptography. Some quantum algorithms like Shah's algorithm could one day break widely used encryption ways by factoring huge numbers exceedingly fast. This has triggered a fresh aspect of security known as post-quantum cryptography, where academics are proposing encryption techniques that even quantum computers can't crack. Still, we're in the early days. Most quantum computers nowadays are noisy, fragile, and limited in what they can perform. The dream developing a fault-tolerant large-scale quantum computer is yet years, if not decades, away. But that doesn't make the voyage any less fascinating. What's really nice is how quantum computing takes the oddest portions of quantum mechanics, the parts that earlier appeared like philosophical puzzles, and turns them into tools. Superposition, once a curiosity, turns a resource. Entanglement, once spooky, becomes useful. Even measurement, that act of reducing alternatives into a single outcome, becomes a step in the computation. It's almost poetry. The very oddity that made quantum theory so unnerving is now being used to solve challenges that were long thought impossible. It's like taming a wild wind, not by battling it, but by sailing with it. Quantum computers invite us to reconsider what it means to compute. They push the limits between certainty and probability, between rationality and fuzziness. They remind us that behind the surface of classical realism lies a much weirder scene, one where information is soft and convoluted and answers arise not from single steps, but from coordinated patterns of possibility. We may not know exactly where this quantum route will go, but the journey itself, subtle, intricate, full of possibilities, is already rewriting our comprehension of what machines and minds can do. In the domain of quantum physics, we anticipate things to be unusual. Subatomic particles teleport past obstacles, spin in two directions at once, and form entangled pairs that speak throughout the cosmos. But there's a location we generally don't expect to observe quantum activity: biology. Biology is filthy, heated, and wet. It functions in a loud universe consisting of jiggling molecules, unpredictable collisions, and variable energy. Quantum effects, on the other hand, are notoriously delicate. They're easily interrupted by heat and turmoil. That's why we develop quantum computers in very cold labs and isolate particles in high vacuum chambers. And yet somehow life seems to be exploiting quantum tricks of its own. Take the robin, for example. A little inconspicuous bird with a remarkable sense of direction. Robins are migratory, flying thousands of miles with uncanny precision. But what's guiding them? How do they know which way is north? Scientists long thought that birds had a built-in compass, but the details of how it operated remained obscure. Then came the radical concept. Quantum entanglement might be implicated. The hypothesis goes somewhat like this. Inside a bird's eye, there may be a protein likely called cryptochrome that carries a pair of entangled electrons. When light reaches the molecule, it excites these electrons, leading them to become quantum-linked. Their intertwined spins then interact with Earth's magnetic field, affecting a chemical reaction in a way that depends on the direction the bird is facing. If that sounds like science fiction, you're not alone. The idea was regarded with suspicion. Entanglement is delicate. Could it truly survive inside a living cell among churning proteins and busy water molecules? Surprisingly, early experiments suggest it might. There's mounting evidence that birds actually do rely on a quantum mechanism to detect magnetic fields. It's not yet entirely proven, but the indicators are good. If true, it indicates nature has figured out how to maintain quantum information in a biological setting. Human engineers are still working to perfect. Now let's shift gears to something green and leafy. Plants, like birds, are masters of a sophisticated quantum game. Consider photosynthesis, the process by which plants use sunlight into chemical energy. It sounds simple enough. Light hits a chlorophyll molecule, which absorbs the energy and transmits it to a reaction center where it's stored. But how does that energy get there so efficiently? You could imagine it jumps aimlessly from molecule to molecule until it reaches the right area. That would be a slow and clumsy process. But measurement shows something substantially more elegant is happening. The energy appears to explore numerous directions simultaneously, as though the system were employing quantum coherence to discover the most effective route. Imagine dropping a marble onto a maze, and instead of rolling down one corridor, it spreads out like a wave, feeling every conceivable way, then decide on the shortest. That's how some researchers believe photosynthetic complexes behave. The energy doesn't travel aimlessly. It takes the best route owing to a bit of quantum navigation. This is striking because these systems are warm, biological, and loud. Yet quantum coherence seems to remain long enough, occasionally on the scale of picoseconds, which in the realm of molecules is a substantial stretch of time, to affect outcomes. If plants are quantum strategists, it poses a tantalizing possibility. Has evolution learned to harness quantum mechanics? There's no reason to suppose biology can't make use of the same principles we discover in physics labs. After all, nature had billions of years to experiment. And creatures that find smart quantum shortcuts, whether for energy efficiency, navigation, or sensing, may have had a survival edge. Speaking of sensing, there's one more biological conundrum that might have a quantum answer: the sense of smell. We normally imagine that fragrance operates by shape. A chemical fits into a receptor in your nose, like a key fitting into a lock, and presto, you detect the aroma. But that theory has some weaknesses. Molecules with similar geometries can smell wildly different, and some molecules with different structures can smell exactly the same. One alternate idea is the vibrational theory of alaction, which reveals that our nostrils don't only perceive shape, they detect how molecules vibrate. The proposal is that when a molecule binds to a receptor, electrons in the receptor might tunnel through the molecule, and the likelihood of tunneling depends on the molecule's vibrational frequency. If accurate, it would suggest that part of your sense of smell involves quantum tunneling, the same trick that helps particles flow through barriers in nuclear fusion. Your nose might be sniffing in stereo, both physically and vibrationally, using quantum mechanics to assist decode the unseen world of molecules. Again, the idea is contentious, although experiments have shown that individuals and even fruit flies can sometimes distinguish between molecules that differ merely in vibrational frequency. It's not definitive, but it's enough to keep experts fascinated. Quantum biology is still in its infancy. Most of the field is developed on bold ideas, tentative experiments, and more questions than answers. But what makes it exciting isn't just the novelty. It's the reminder that the peculiar principles of quantum physics don't stop at the lab bench. They stretch into the feathers of birds, the leaves of trees, and the breath you draw via your nose. It's a humbling concept. The same mathematics that governs the behavior of electrons in a vacuum also underpins the chirping of a robin and the glitter of sunshine on a leaf. Nature doesn't separate its domains. Quantum effects aren't stored away in some minuscule vault. They're everywhere, entwined into existence itself. And perhaps as we grow to grasp these quantum tricks, we'll gain not only new technologies, but a deeper respect for the creativity of evolution. Life, it seems, has always been playing with the oddest tools in the world. They just never bothered to tell us. At the quantum level, particles do strange things. They blur into super places, interfere with themselves, and occupy numerous possibilities all at once. It's the playground of likelihood, not certainty. And yet, when you glance around, you don't see a planet composed of shimmering May. You see a coffee mug, a desk, a cat, hopefully living or dead, but not both. You engage with a universe that seems solid, reliable, and gloriously predictable. Why is that? Why don't you notice tables that are both here and over there? Why don't full sandwiches appear in a probability wave only collapsing when you open the fridge? The answer rests in a modest but powerful process called decoherence. The process that explains how the quantum world progressively loses its quantumness and becomes the classical reality we know. Let's start with a little mental stretch. Imagine a single electron in a superposition. It's not in one spot. It's among a range of options. You can't say exactly where it is until you measure it. And even then, you're merely urging it to choose a location. Now imagine that electron is left alone in the vacuum of space, utterly separated. It remaining in that gorgeous, delicate super posture. But back on Earth, things aren't so tranquil. There's air, heat, photons from the sun, molecules bouncing about, vibrations, fields, and background radiation. The moment your quantum item interacts with any of this, it begins to lose its quantum coherence. The clean mathematical interference patterns start to fade. This is decoherence. It's not that the superposition evaporates. It's still there in a way, but the quantum system becomes enmeshed with the environment. That is, all those particles it touches become part of its quantum description. And when that happens, the system ceases behaving like an isolated wave of probability and starts behaving like something common, predictable, measured. You can think of it like this. Quantum systems aspire to remain private, but the moment the environment peeks in, they lose their privacy. Not because someone measured them with expensive equipment, but because nature itself is always monitoring. Air molecules, photons, vibrations, all these things function like tiny constant observers. They don't collapse the wave function, rather they blur out its coherence, making interference impossible. Decoherence is a subtle decay, not a violent snap. It doesn't require a conscious observer or a big dramatic measurement. It just requires time and interaction with the outer world, and it happens really fast. For tiny things like electrons or atoms, you can isolate them effectively enough that quantum behavior lingers around. But for macroscopic items, things you can touch, see, or consume, decoherence happens almost instantly. The more big and intricate the system, the faster its quantum oddity transforms into classical certainty. In fact, decoherence timescales for huge things can reach trillions of a second or less. That's why you don't walk into a room and discover your shoes in a quantum fog. Their engagement with the world has already pinned them down to a specific state. In this method, decoherence doesn't ruin quantum superpositions, it hides them. The superpositions still exist in concept, but they're now enmeshed with so many environmental degrees of freedom that you can't access or reverse them. They become effectively classical, even while deep down everything continues quantum. This also helps explain one of the long-standing riddles in quantum mechanics. How do we get from probabilities to outcomes? Decoherence doesn't answer this puzzle altogether. It doesn't decide which outcome occurs, but it helps explain why we don't witness quantum interference in huge systems. Why Schrödinger's cat, if left unnoticed, doesn't genuinely waver between life and death on your kitchen counter. Decoherence gives the illusion of collapse by bleeding quantum information into the surroundings. The result is a kind of statistical consensus. The wave function is still there, but it no longer behaves in a coherent, visible way. And this affords us a bridge between the quantum and classical worlds. Classical physics is still a useful tool. It's how we build bridges, launch rockets, and make solids. But beneath it all, the universe hums with quantum rhythms. What decoherence does is softly conceal that underlying oddity, providing the robust world we experience. One useful way to envision it is like strolling on a frozen lake. Beneath the surface lies water, moving, fluid, quantum. But the ice is firm and reliable. Decoherence is what freezes the surface. It doesn't eliminate the water underneath. It only keeps it out of reach. And the more connected an item is to its surroundings, the thicker that ice gets. This also has practical consequences for technology. Quantum computers, for instance, have to fight decoherence constantly. Their qubits are fragile, and even a stray vibration or heat fluctuation can collapse their quantum characteristics. That's why they're kept in ultra-cold confined locations to extend their coherence as long as possible. Without that, the quantum advantage vanishes. Decoherence also has a function in interpretation. Some ideas indicate that there's no necessity for a distinct collapse of the wave function. Instead, decoherence explains why certain outcomes appear definite. It's not that the cosmos chooses an outcome. It's that the alternatives become unobservable because to entanglement with the surroundings. The tree still falls in the forest, but its echo is drowned out with loudness. It's worth stressing decoherence doesn't solve every riddle of quantum mechanics. It doesn't answer why a specific measurement gets a particular result. It doesn't tell us if the wave function is real or just a mathematical tool, but it does explain why quantum strangeness dissolves into classical certainty in ordinary existence. It teaches us that the world we perceive is not different from the quantum domain. It's shaped by it, mediated via continuous interaction with everything around us. So the next time you pick up a mug or open a door, you may credit decoherence for the fact that it behaves the way you expect. for taking a universe of May and presenting it as a solid handshake. It's a silent phenomenon. No sparks, no sparkles, just the steady, beautiful fading of possibilities, leaving behind the fixed patterns we call reality. Imagine setting up an experiment so unusual, so delicate that the sheer act of deciding when to observe seems to reach back in time and alter what happened previously. It sounds like science fiction or even science misunderstanding, but this is precisely what happens in a sequence of experiments that tamper with the basic premise of cause and consequence. They go by names like the delayed choice experiment and the quantum eraser. And if you're thinking quantum physics would finally start making sense, well, this is the point that even time itself starts to shrug. Let's begin with a common arrangement, the double-slit experiment. Fire a beam of photons or electrons or even molecules at a wall with two slits. Behind the wall is a screen to catch what comes through. If you don't know which slit the particles go through, they generate an interference pattern, a succession of light and dark bands, as if each particle went through both slits and interfered with itself. But if you set a detector to discover out which slot each particle goes through, the interference disappears. The particles operate like miniature bullets instead of waves. Simply knowing the path destroys the wave behavior. So far, so weird. Now let's go wicked. In the delayed choice experiment, originally proposed by physicist John Archibald Wheeler, you put up your experiment without measuring the particle's journey, but you reserve the right to decide whether you'll measure after the particle has already passed through the slits. In other words, you defer your choice. Will you act like a nosy detective and observe the path, or will you let the particle remain mysterious and wave-like? Here's where it gets surreal. The pattern on the screen will match whatever option you make, even if that choice comes after the particle has apparently determined how to behave. It's as though the particle somehow knows what your future choice will be and adjusts its prior behavior accordingly. Either it produces an interference pattern, wave behavior, or it doesn't, particle behavior, dependent on an event that hasn't even transpired yet. It's enough to make a clock melt. This experiment demonstrates that the quantum universe doesn't commit to a specific reality until it's pushed to. Not just in space, but in time. The act of observation doesn't merely decide the outcome. It might determine the history. And then quantum physicists added, let's make this even weirder. Enter the quantum eraser. In this twist in the double-slit arrangement, you mark the particles so you can know which path they went, but then you utilize a clever way to remove such information after they've been found. And when you do that, when you eliminate the which path info after the fact, the interference pattern comes back. The particles act like waves again retroactively, as though they never gave up the ghost of uncertainty. This raises a deeply frightening idea. Reality might not be finalized until all possible information is settled. Not simply the time of detection, but also the moment we determine what to do with the knowledge regarding that detection. It's like a cosmic version of Schrödinger's cat, but extended throughout time. Not only is the cat both alive and dead, but whether it was alive or dead depended on a decision made after you opened the box. So what's going on here? One tempting interpretation is that information, not physical things, is the fundamental currency of the universe. In the quantum universe, outcomes aren't locked in until you ask questions that have answers. Until then, all options remain intertwined in a murky soup of May. That doesn't mean time travel is real or that we can modify the past. Rather, it suggests that our usual image of time as a one-way street might not apply at the quantum level. Events in the quantum realm aren't linked together by neat linkages of cause and consequence. They're part of a bizarre holistic web where outcomes emerge only when a complete system is considered. Still, there are restrictions. While these experiments are remarkable, they don't allow for communication with the past. You can't send messages backward through time or change what previously transpired. The results always play by the principles of causation at the large-scale level, but they imply that under the surface such rules are a bit more flexible. Some physicists explain it in terms of entanglement and correlation, not causation. The particle doesn't know what you'll do in the future. It's only that all the elements of the experiment are interwoven in such a way that your final setup defines what patterns are visible. Others lean into a block universe view where all moments in time exist simultaneously, like frames in a film reel. In this standpoint, your choice isn't anything that travels backward. It was always part of the vast, everlasting quantum narrative. And still others shrug and say, "Shut up and calculate." The main thing is this. The world is under no duty to conform to our common sense concepts of time, cause, or measurement. Our classical intuitions are developed from macroscopic objects, rocks, and coffee cups and cats. But down in the quantum mist, the rules are subtler, less linear, less local, and much, much stranger. The delayed choice and quantum eraser experiments don't break physics. They expose the richness underlying it. They prove that the quantum world is not merely a smaller replica of our ordinary world. It's something profoundly different playing by a logic all its own. So if time ever feels like it's playing tricks on you, just remember on the quantum level, it probably is. If you were to zoom deep enough into the heart of the cosmos, past the galaxies, past the molecules, past the atoms themselves, you'd eventually arrive at a world where certainty slips silently through your fingertips. A world where outcomes are not determined, but described in terms of probability, where particles don't have placements until you look. And even then, they're only the outcome of a cosmic dice roll. Welcome to the quantum universe, a place that's not just small, it's unpredictable. At its essence, quantum physics suggests that randomness may not merely exist, but may really rule. This idea doesn't sit comfortably with everyone. In fact, it made Albert Einstein notably uneasy. He famously remarked, "God does not play dice with the universe," a line that's been cited for nearly a century in every philosophical cafe conversation involving physics and fate. But let's unpack what this unpredictability actually means and what it doesn't. In classical physics, everything behaves like a well-oiled machine. If you know the position and velocity of every particle in a system, you can forecast the future with exact precision. It's a neat deterministic framework like setting up dominoes and knowing exactly how they'll fall. Quantum mechanics destroys that chain. It replaces precise forecasts using wave functions, mathematical objects that explain all the conceivable consequences of a particle's action. And when you make a measurement, the wave function collapses into one of those possible consequences. But which one you get isn't determined ahead of time. It's genuinely random. That's not a code term for "we just don't know" yet. It's not the product of human error or insufficient information. It's baked into the structure of reality itself. The best you can do is calculate the likelihood of each outcome and accept what shows up. Now, several interpretations of quantum mechanics, like the many worlds concept, avoid this randomness by arguing that every possible scenario does happen, just in a separate branching world. So when you measure a particle and it spins up, there's another version of you in another reality where it spins down. No randomness, only endless outcomes. But even if that's true, you still can't guess which version you'll find yourself in. From your point of view, the experience is equally as uncertain. This raises some deeply philosophical questions. If randomness exists at the base of existence, what does that imply for cause and effect, for free will, for the rules of nature themselves? It could feel disconcerting at first. The concept that the universe isn't operating on some big script but improvising along the road. That there's a basic looseness in the weave of reality. And yet randomness isn't the same as pandemonium. In reality, quantum mechanics is incredibly precise in its projections. It doesn't say anything could happen. It says here's a list of what can happen and the probability of each. When physicists tested quantum predictions like those from quantum electrodynamics, they found agreement with experiments to 12 decimal places. That's like estimating the height of Mount Everest to within the width of a human hair. So even if quantum outcomes are unpredictable, the structure of that randomness is highly orderly. It's a bit like rolling a 100 dice and discovering that they always sum to a predictable average. Even if each die lands randomly, the outcomes are probabilistic. But the behavior of enormous numbers of particles becomes so dependable that it gives rise to the laws of classical physics. This is why your coffee mug doesn't suddenly tunnel through the table, even if individual particles may. In this sense, unpredictability is not a bug. It's a feature. It adds flexibility to the universe. It allows for uniqueness. It might even be vital for life, creativity, and consciousness. Think about mutation in evolution. If every biological occurrence was strictly determined, there would be no variation, no branching routes. But put in a little randomness, a modification in a gene here, a transmutation there, and suddenly the universe has possibilities. Some of those possibilities lead to leaves, some lead to leopards, some lead to philosophers. In the quantum domain, randomness is the engine of variety. It gives rise to complexity from simplicity. And it does such without breaching the laws, since the principles of quantum mechanics are probabilistic, not prescriptive. Some scientists and philosophers take comfort in this unpredictability. After all, a deterministic universe can seem like a clockwork jail where every thought, action, and feeling is just the echo of particles obeying tight principles. But a probabilistic universe, that's one where the unexpected can happen, where results aren't etched in stone, but picked from a deck. Of course, randomness also comes with mystery. When we detect a particle in one condition rather than another, why that one? Quantum mechanics doesn't offer a rationale. It just provides you the odds. It's like flicking a coin and getting heads. There's no deeper reason for the event, merely that it had a 50 chance. And this has philosophical weight. It suggests that the universe is not fully knowable in the classical sense. There's a ceiling to assurance, a boundary beyond which questions don't have definite answers, only ranges of possibility. And yet, we may still thrive in that uncertainty, build technology from it, discover meaning in it. Quantum randomness also ensures that no two objects are actually similar. Even particles prepared in the exact same way will sometimes yield various outcomes. This small imperfection, this whisper of surprise, is what keeps the universe alive and intriguing. So perhaps the world does play dice, not carelessly, but with an elegance so sophisticated that it creates galaxies, atoms, thoughts, and time itself. And while we may never entirely harness that randomness, we might grow to respect it not as a weakness in the cosmic mechanism, but as the subtle hum of possibilities threaded throughout the fabric of everything. If quantum physics were only a set of equations, however weird, however exquisite, it may still be deemed one of humanity's greatest intellectual achievements. But what makes it actually unique is that it doesn't merely describe particles and probabilities. It invites us to reflect on something deeper, what it means to know and what it means to be. Because while peeling back the layers of the universe, quantum physics doesn't just reveal fresh answers. It reshapes the questions themselves. We prefer to think of reality as something concrete, fixed, out there, something that exists whether we're here to look at it or not. But the quantum world disagrees gently yet persistently. It indicates that at the smallest level, reality isn't fixed at all. It's a bundle of possibilities like dreams waiting for a spectator to nudge them into form. When a particle exists in a superp location, it's not just undecided. It's all its conceivable states at once. A smear of likelihood, not a single up. And when we measure it, it settles on one outcome, as though the cosmos slowly breathed and chose a story. This raises the quiet, uncomfortable thought. If observation has such a key role in affecting outcomes, are we as distinct from the universe as we formerly believed? Or are we watchers? Is everything a part of the huge intertwined dance? For physicists, these are technical questions. For the rest of us, they feel almost spiritual. But quantum science isn't here to deliver easy answers. is not a shortcut to enlightenment or a metaphor factory for self-help books. And yet it does leave us with something important: humility. It reminds us that our everyday intuitions about space, time, substance, and cause are not the ultimate word on how things work. That the familiar world we navigate each day is merely one form of reality filtered via evolution, molded by our senses and sewn together by habit. In this sense, quantum mechanics becomes more than physics. It becomes a mirror showing us the edges of our knowledge, the limits of our understanding, and the astonishing mystery of the universe we call home. Think of Schrödinger's cat, not as an actual feline locked in a contradiction, but as a metaphor for the way we live in ambiguity, for how we continually juggle contradictory possibilities, half-knowns, and almost certainties. Whether it's waiting for a medical test result, applying for a job, or merely wondering if it will rain tomorrow, we reside quite often in a quantum state of our own. Hope and dread, expectation and doubt. Possibilities piled lightly over each other until time or decision collapses the wave. And maybe that's the secret beauty of quantum mechanics. It's not informing us that the world is unknowable or pointless. It's merely telling us that it's not bound to be obvious. There's a softness to that awareness, a peaceful release. If certainty isn't assured, then neither is limitation. If the world isn't pinned down until it's observed, then potential is always alive, flickering just out of view. Even the word quantum has a kind of poetry to it. It derives from the Latin quantus. How much? How much light? How much energy? How much is this or that particle allowed to be or do? But more than that, it's a word that points toward boundaries, distinct indivisible packets, the smallest permissible unit of change. And maybe there's something profound in that too. That even in the immense and swirling complexity of the cosmos, there are boundaries, minimal steps, quiet thresholds that must be crossed. Not everything is continuous. Some things change in leaps. When you dream, you don't do it one atom at a time. You leap into universes that don't exist until they do. You witness impossible things until they feel natural. And when you wake, you may not recall all the rules, but you carry back the feeling of possibilities. Quantum physics feels like that, like waking from a dream and realizing that the world is stranger, wilder, and more wonderful than you'd ever expected. Of course, this can be a little unsettling. We like cause and effect. We like knowing. Certainty has its comforts. But maybe it's also a touch overrated. Maybe it's good to live with questions that don't yet have answers. To roam in a thicket of probabilities without demanding to know which tree is real. Maybe that's where wonder resides, in the voids between what we can grasp and what we can only see. Physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant it as both a joke and a truth. Even those who work with the arithmetic every day, who develop devices and models from its predictions, will admit that quantum physics is not something you get in the regular way. It's something you embrace like a poetry or a dream. It works. It's precise. It's testable. And yet, it refuses to be tied down by everyday logic. And maybe, just maybe, it makes it more honest since the universe was never compelled to be simple. It just had to be. So, as we float now through the silent ripples of quantum thought, maybe the most essential lesson isn't about particles or probabilities, but about perspective. To perceive uncertainty not as a problem, but as a feature. To let go softly of the need to know everything, and to rest in the weird, wonderful truth that we are part of a cosmos that is still unfolding, still choosing, still glittering with promise. A place where even the emptiest vacuum isn't truly vacant. Where time may flex, where light forgets how to behave, and where in the end reality dreams too. Thank you for listening. Whether you're still wide awake, drifting slowly, or already halfway into a dream, we wandered a long distance tonight through slits in cardboard, thought experiments with cats, rippling fields, and mysterious erasers of time. We've considered particles that behave like waves, waves that act like particles, and forces that play by rules written in a language we're only just learning to translate. And somewhere along that voyage, we began to see not simply the oddness of the quantum universe, but its peaceful beauty. At first sight, it might all seem too odd to be genuine. A universe where something isn't truly anything unless it's observed. Where causation and effect get hazy around the edges. Where a particle can be here and also somewhere else. But what quantum physics softly informs us over and over again is that the reality we know, the one we can touch and taste and measure, is simply the surface. Beneath it lies a gentler world. Stranger, definitely, but also more flexible, more open to surprise. A universe created not on certainty, but on shimmering potential. And we are part of that world, not separate from it, not merely observers looking in from the outside. We are built from these identical quantum forces. The atoms in your fingertips, the light that reflects from your eyes, the oxygen in your lungs. All of it obeys the same dubious laws. You are not merely in the universe. You are of it. And doesn't that feel just a little bit poetic? Back at the start, I asked location in the world you're listening from. Maybe you're wrapped up in bed, listening under a heavy cover. Maybe you're gazing at the ceiling, ideas twinkling like stars. Maybe you're distant from home or merely far from sleep. Wherever you are, I hope you discovered something in this voyage, anything gentle or odd or simply still. And remember that when we delve into the heart of matter and ask, what is real? Quantum physics doesn't offer us a final solution. It provides us a mirror, moving one. A reminder that knowing something intimately doesn't always entail understanding it entirely. That questions might be as lovely as answers. That mystery is not a failure, but a feature. It can be tempting to yearn for more clarity, to want the cosmos to spell forth its rules simply and play fair. But maybe amid this tangled uncertainty, there's a new kind of comfort, a soothing truth that says you don't need all the answers to feel at home here. Because even if the particles are unclear, the moment you're in is genuine, the breath you just took, the thought that just drifted by, the weight of your body softly sliding into quiet, that's quantum too. And it's enough. So thank you for giving your time, your ears, and your calm inquiry to this little exploration. For trusting the strangeness, for sitting with a not knowing. And if you've already fallen asleep, amazing. The quantum world will still be present when you wake. From the sleepy scientist, good night.